city on average is in microsecond. Suppose there are n cities. Any guess? What is the possible time? Any guess? See, it takes microsecond from one city to another city between pair of cities on average. So if there are 10 cities, any guess? No guess. So it is within second. Can you see it? No.
Yes, sir.
Okay, fine. Suppose n is equal to 12. Any guess? Rough guess? N is equal to 12. Rough guess? Any rough guess? No? It take 20 seconds. N is equal to 15. Any guess? Any rough guess? You just see 12 hours. If n is equal to 20, it take 19 years. So you can understand the complexity of the problem. And this is the classical problem. So if it take 19 years, who is going to solve this problem? So to find some solutions, we take some what you call approximate solution depending upon requirement. Suppose I don't need exact solution, I need approximate solution. It takes, let's say, 2 days or 3 days. It is good enough for me as compared to 19 years. So I will go for that. Now, if it's the early developments regarding optimization or calculus especially, so Bhaskara second in 1114 and 1185 introduced some idea of differential calculus. 12th century. He also goes deeper into the differential calculus and suggests that differential coefficient vanishes at an extremum value of the function. This is where minima or maxima occurs. So Bhaskara second discussed long back about the maximum or minima, which called extremum value, indicating a knowledge of the concept of infinitesimal. There is evidence of early form of Rayleigh's theorem. Rayleigh's theorem you must be knowing. If there is an interval in which f is defined, f a and f is equal to 0, it means there exists some point where the derivative of f is parallel to x-axis. It means derivative of f with respect to x is 0 in that interval. That is called Rayleigh's theorem. So this idea also was given Bhaskara 2. Solutions of quadratic equations, cubic or quartic intermittent equations also explain. Indeterminate means there is a single equation and having multiple variables. Those are called indeterminate equations. For example, ax square plus bx plus c is equal to y. This is a single equation, but it has got two unknowns, x and y. So this is the indeterminate equation. The solution of this equation was attributed to Broncker in 1651. Though this method was more difficult than the Bhaskara, Bhaskara gave the solution of this long back. And 1657, another solution was given by Broncker. The first general method to find the solution of the problem x square minus ny square is equal to 1, which is known as Pale's equation, was given by Bhaskara. So long back, mathematicians in India, they defined optimization, calculus, even differential calculus and integral calculus, all those, they defined long back. Solutions of Diophantine equations of second order, such as 61x square plus 1 is equal to y square. This is also same indeterminate equation. There are two variables and single equation. This very equation was posed in 1657 by Fermat, and its solution was unknown in Europe till 19th century when Euler discussed this problem. But this problem was solved long back. in 12th century itself. But the world did not know this. He provided solution to quadratic equation with more than one unknowns, also found negative and irrational solutions also. He gave basic concept of infinitesimal calculus, which is also known as differential calculus or integral calculus. The mean value formula for inverse interpolation of sine was founded by Parmeshwara in 15th century, Mahadevan in 14th century, and Kerala school, which include Parmeshwara from 14th century to 16th century, expanded the Bhaskara work. The Fermat was then 1600 to 1665. A French mathematician led to the development of infinitesimal calculus, which is called differential calculus or integral calculus. See, you can understand the Europe understood this calculus in 60s, 70s, but it was long back known in India in 12th century itself. He developed a method to find the greatest and the smallest ordinates of the curved lines, which is now known as differential calculus. He contributed to analytic geometry, probability, optics to solve the various problems. Simple example of such problems is to find the curve of shortest length connecting to point. See, if there is a straight line, then there is no constraint. Then a straight line will be the shortest path between 2 points. If there is a constraint, then shortest path may not be the straight line. It might be some curve, and that curve may not be unique. And such solutions are called geodesics in high dimensional geometry. The problem, uh, the problem of maxima minima, a book written by Ramchandra Lal, 1821 to 1880, was promoted by De Morgan. You must be knowing De Morgan. He was a great mathematician. In his preface to this book, De Morgan states that Ramchandra was born in about 1820 in Panipat to Sundar Lal. He came to De Morgan's attention in 1850s when a friend of his sent him the Ramchandra's work on maxima minima. See, Ramchandra also developed this maxima minima. He was a self-taught mathematician in 19th century. De Morgan was so impressed that he arranged the book written by Ramchandra to republish in under his own supervision, and in general undertook to bring Ramchandra work to the notice of the European scientific community. He quotes, De Morgan says in the preface of this book, on examining this work, I saw in it the encouragement of which, not merely the merit worthy of the encouragement. See this point, not merely the merit worthy of encouragement, but the merit of peculiar kind, as it appeared to me. See, even a Demorcus was not able to understand things very properly. So was likely to promote native efforts toward the restoration of the native mind in India. Now let us come to the quadratic form. The quadratic form is a polynomial having all the terms of degree 2. It is called a homogeneous polynomial. It has many applications. In physics, the quadratic forms are used to describe the motion of the object under influence of the forces, equation of motion or equation of projectile. Engineering, they are used to analyze the stress and strain in materials, especially material science, in control system to model the dynamic systems. Economics and finance, they are used to model the optimization problems such as maximizing utility or profit subject to constraints to find the optimal allocation of assets. Computer science, they are used machine learning like support vector machine, etc. Image and signal processing, they are used for tasks like image comparison, denoising, feature extraction. Statistics, they are used for estimating the parameter in regression, analysis and hypothesis testing, relationship between the variables, correlation basically. Robotics, they are used in robotic motion planning and control and to optimize the trajectory for the robotic systems. So, a quadratic form f of x is Rn to R is a function. F take the vector and it gives 2x transpose qx, where q is a real matrix. See, we can assume q is a symmetric. Even if q is not symmetric, we can make it symmetric. See, x transpose qx, it is a scalar. If I take the transpose of this, it is again a scalar, because transpose of a scalar is a scalar. So if I take the transpose of this, I will get 2x transpose q transpose x. Now you add them. F of x is equal to x transpose qx plus x transpose q transpose x. So you take q plus q transpose is the symmetric matrix, right? Hello? See, you have to respond in between. Otherwise, really don't feel whether something is going on. So q and q transpose is symmetric. So we are assuming 2x transpose qx. In this case, it is q is symmetric. Even if it's not symmetric, we can make it symmetric by using half q plus q transpose. Now, a quadratic form x transpose qx, q is equal to q transpose, is said to be positive definite. See, first question is why we need this positive definite, negative definite, semi-definite, etc. See, when you do maximization, minimization, you must have read in your 12th class or 11th class to differentiate the function itself and make it zero. Whatever value you get, use that value and calculate the second derivative of the function. If the value of second derivative of the function at that point, which you have obtained from the first derivative, greater than 0, it means the function has got minimum value at that point. If second derivative of the function at that point is less than 0, it means f has got the maximum value at that point. So, in case of scalar, it is very well defined. Take second derivative, take first derivative, make it 0, you will get some value of the variable. Then you take the second derivative, evaluate the second derivative at that point. If it is positive, it is minima. If it is negative, it is maxima. Now, if you take the vector form, not the scalar, in that case, the Q matrix is very important. So if x transpose qx greater than 0, we say q is positive definite. In other words, if all the eigenvalues of q are positive, then we say this form of q itself is positive definite. It is equivalent to saying that second derivative greater than 0. It means for minima, q should be positive definite. It is positive semi-definite if x transpose qx greater than equal to 0 for all eigenvalues of q are non-negative. See, x transpose q is semi-positive definite. It means the eigenvalues of the q are non-negative for all the vectors. A quadratic form x transpose qx is said to be negative definite if x transpose qx less than 0 or all eigenvalues of q are negative. It is called negative definite. Negative definite means in terms of second derivative. So we have to see only q, because this, if I differentiate f of x with respect to x, I will get some function, make it 0, I will get some value of x vector. Take the second derivative. If you take the second derivative of f, you will simply get q only. So if q is positive definite, it means f has minima at that vector point. If q is negative definite, then f has maxima at that point. Point is not a single point, it is a vector now. Now, can you see the example q is equal to 1, 0, minus 4, 1? It is not symmetric. So what I will do, I will make first symmetric, take the transpose of this, add them and divide by 2. So you will get 1 minus 2 minus 2, 1, which is symmetric. Now if you see this, whether it is positive definite or negative definite, you can calculate the eigenvalue of this. If all the eigenvalues are positive, then it is a positive definite. If all eigenvalues are negative, then it is negative definite. So in this case, any comment, you can find out the eigenvalues of this. Now, there is a simple example. F of x is equal to 3x1 square minus 5x2 square plus 9x1 x2.
So your audio is
Hello?
mute. Yeah.
Sir, audio is muted. Judges.
It is okay now?
Yes,
Yes,
sir.
sir.
See, I did not do anything.
Now it's fine.
I don't know how it happened. See, this is the given function f of x is equal to 3x1 square minus 5x2 square plus 9x1 x2. And it is from R to R. To means we are considering vectors, not the scalar. R to R. Now I have to write this in terms of x transpose. If you go to the previous slide, I have to write f of x in terms of this. Can you see this? Quadratic form 2x transpose qx. I need to write this fx in terms of x transpose qx. So the matrix Q will be 3, 9 by 2. This is the first row. Second row 9 by 2 minus 5. So it is a symmetric matrix itself. Now you have to check whether it is a positive definite or negative definite. Then you have to find the eigenvalues of this. If all the eigenvalues are positive, then it is a positive symmetric matrix. If it is a negative, all eigenvalues are negative, then it is a negative definite. It means for positive definite, it has got the minima, and for negative definite, it has got the maxima. Now, can you see the second example? X transpose minus 1, 3 minus 2, 4, x.
Yes, sir.
Here Q is minus 1, 3 minus 2, 4. It is not symmetric. You have to make symmetric. Take the transpose of this and add it. This and this transpose and this symmetric, then add them and divide by 2. So how much it comes out to be? Any idea? Minus 1, 3 minus 2, 4. This is the matrix. And take the transpose, add both the matrices and divide by 2. Then whatever matrix you get, you will get the symmetric matrix. Then you find the eigenvalue of that matrix. If all the eigenvalues are positive, it is positive definite. If negative, it is negative definite. Now, we define the matrix norm. Norm means we need to find the scalar quantity corresponding to a matrix. So it is induced by the norm vector x defined as max of norm ax. Ax is a vector now. A is a matrix. X is a vector. If I multiply a matrix by a vector, I will get a vector. So if I consider vector, I will take the norm. And constant is, it is a unit circle. What you call unit sphere or unit hypersphere, whatever call it. Norm x is equal to 1. You have to find the maximum value of ax within a what you call hypersphere. So we define a norm vector x is equal to k is equal to 1, x power k square, and this is called L2 norm. And it is defined x comma x or dot product to itself. The matrix norm induced by this vector is given by this. If you see this, norm of A is equal to square root lambda 1. Lambda 1 is the maximum eigenvalue of matrix A. A transpose A. Because A may not be a square matrix, but A transpose A will always be the square matrix. If it is a square matrix, then we can find the eigenvalues. For n cross n real symmetric positive definite matrix, we have a one constraints or what you call lemma, minimum eigenvalue multiply norm of x less than equal to uh, quadratic form less than equal to maximum eigenvalue and norm of the vector, where P is the matrix and lambda minimum is the minimum eigenvalue, lambda max is the maximum eigenvalue of the P. And this is called Rayleigh inequality. This, the value of this quadratic form will lie between lambda min and lambda max, not beyond that. There is one important theorem, Weierstrass theorem. It says f is a continuous function only, not more than that. We are not considering even differentiability also, where omega is the subset of Rn which is compact. Compact means it is closed and bounded. Then there exists a point x0 in the omega such that f of x0 less than f of x for all x belong to omega. It means there exists a minima point. Suppose you consider a function that does not have a peak. Does it have a maximum minima? Suppose you have a function defined some omega. In the omega, it does not have peak inside the omega. Does it have maximum minima? Hello? Does it have maximum minima? It is simply a continuous function. No other condition, differentiable, etc. Nothing is there. Will it always have the maximum minima? Hello? No comment? See, it will always have the maximum minima. It will always have the maximum minima, whether it has a peak or not, peak or valley, whatever you call it.
Okay, sir.
Now, f is a function from Rn to R which is differentiable, and its first derivative defined by df is del f transpose. df is the total differentiation of f. Capital X the vector. Please try to understand. It is not a simply a scalar. It is a vector now. The total derivative of a function f is perpendicular to the gradient of the function. That's why it is transpose. Can you see df x is equal to del f x transpose? Can you see it? Yeah.
Yes, sir.
So total derivative is always perpendicular to the gradient. So we are very much interested in gradient. The vector del f of x is called the gradient of f, which is a function from Rn to Rn. See, in case of scalar function, we take the first derivative, make it 0. But in case of vector, if f is defined from Rn to R, it takes the vector as an input and give the scalar. In that case, it is the derivative is not a scalar, it is a gradient. And gradient is same as first derivative in some sense. The first order derivative and the gradient are perpendicular to each other. You have to keep this in mind. If del f gradient is differentiable, then we say f is twice differentiable, and that differentiation is called Hessian matrix. It is same as the second derivative f. In case of scalar, you get a single quantity. In case of Rn to R, we get a matrix. So f is d square of f x, and it is all second derivatives. And this is called Hessian, and Hessian matrix is always symmetric. And it is symmetric only when f is continuously differentiable 2 times. F belong to C2. If f is not C2, then it need not be symmetric. Please try to understand. The function has to be twice continuously differentiable. If f is not twice continuously differentiable, then f need not be symmetric, even though the formula seems to be quite symmetric. For example, first term you can see del 2 f of x upon del x1 square, del 2f of x, del x2, del x1. And you see the second row, first element, del 2f of x, del x1, del x2. They are equal only when f is 2 times continuously differentiable. If it is not, then they are not same. It is very important property. Now, let A be a matrix of size m cross n, and y is a vector of dimension m. Then differentiation of y transpose A x is y transpose A. We are differentiating with respect to x. D differentiation of x transpose Ax is equal to x transpose A plus A transpose. If A is symmetric, then we can write differentiation x transpose Ax is equal to 2 times x transpose A. Now, you must have read somewhere there is a expansion, Taylor series expansion. In case of scalar, you have f of x is equal to f of x naught plus x minus x naught, f dash, f dash x, and x minus x naught plus 1 by factorial 2, f double dash x naught, x minus x naught ka square, and so on. But in case of x is a vector, then you have to be very careful. It is f of x naught is the vector with respect to 1 to expand as a Taylor series. It is d f of x naught, x minus x naught plus half x minus x naught transpose d square f of x naught, x minus x naught. D square f is the Hessian. Given an optimization problem with constraint set omega, a minimizer may lie either in the interior or on the boundary also. See, if there is no peak, then interior maximum minimum will lie on the boundary. If there is a peak or valley, then minimum and maximum is inside, interior to the domain where it is defined. If it is a smooth straight line or something like that, then it can lie on the boundary. See, what we do in first derivative, make it 0, and second derivative greater than equal to 0. But if lies on the boundary, then these conditions may not hold. They are applicable only when the maximum minimum lies in the interior of the domain where the function has been defined. If it lies on the boundary, then we have to see something else. If the maximum minimum lies on the boundary, then we need the notion of feasible directions. See, in that case, we need the direction. If the maximum minimum lie on the boundary, then we need to see the directions where it is defined. If vector d belongs to Rn, d is not equal to 0 is called a feasible direction at x. If there exists alpha greater than 0 such that x plus alpha d belongs to omega for all alpha belongs to that domain 0 comma alpha 0, only then we will say this d is the feasible direction. X plus alpha d belongs to omega. The entire vector x plus alpha times the direction should lie in the domain itself. If it is outside, then it's not a feasible direction. Okay. Can you see the example? A transpose x, B transpose x. Here we
Yes,
are
sir.
Yes,
n-line
sir.
vector.
Yes, sir.
Sir, I have a question. May I interrupt for a second?
Yeah, please.
Sir, here there's an operator d
Please go
square you're
ahead.
using, right? D square, the operator that you're using here,
Yeah.
that's the second order derivative of the vector, right? So is that the Laplacian operator, del dot del?
Yeah, please spell out. I'm not able to get it.
Hello, sir,
Yeah,
are
yeah.
you able to hear me?
Yeah, please.
So what I'm asking is that in this above equation where we have the Taylor series expansion,
Yeah.
we have d of f of x naught, right? Now d is in the previous slide you had explained that it is del operator, right?
Not
Uh,
developed. See, is it transpose? Can you see it?
yes, sir.
Second line, d of
Sir,
f is equal to del f transpose.
right, del f transpose, correct.
Yeah.
But this del is the del operator, right?
Yeah.
That's a partial derivative with respect to x,
Yeah.
y, and z. Now,
Yeah.
what I'm asking is that when we say d square, are we
Yeah.
talking about del dot del, which is the del squared or the Laplacian operator?
No. Second derivative of this vector itself.
Okay. Okay, sir.
See, first derivative is like this. You can see this. Then
Right.
each of the component has to be differentiated with respect to all the variables.
Okay.
Only then it will be the matrix. Otherwise, it will not be a matrix.
Okay, sir.
And this is what you have got, f is equal to d square f of x.
Okay. Second, that means we have to differentiate it twice.
Yeah. Each vector, each
vector.
component is absolute each element of the
Yes,
vector.
each partial derivative we have
Yeah,
to
yeah.
take for x1, x2 respectively. Correct.
Yeah.
Thank you, sir. Thank you.
Okay. So can you find the gradient of this function? A transpose x, B transpose x. A, B are n-dimensional vectors. Of course, x is also vector. So can you find the del of this? A transpose x, B transpose x. Any guess? Differentiation, which you have been doing since 12th class. A transpose x, B transpose x. You need to find gradient of f of x. Gradient of f. Can you help me to find the gradient of this? Hello? Can you find the gradient of this function? F
So
of
this
x equal.
x is only it's only in one variable.
No. X is vector.
It's a vector.
A transpose x or B transpose x.
And it has components x1, x2, x3.
Yeah. Vector. It is vector.
So
Column vector rather.
we take partial derivatives with respect to x1.
Tell me what the value of this?
Oh, I need to see the function then.
A transpose x, B transpose x. That's all. You have to differentiate with respect to x. Once you get the first derivative, I can take the transpose, I will get the gradients. But how to get the first derivative? Tell
x
me
to
a
the
simple
power
function.
x to the power n-1 over nx to the power n-1.
No. This is A transpose means transpose of vector A multiplied by x, B transpose x. You have to differentiate this function with respect to x. It is not a power, it is a transpose. So any guess? Anyone can help me to find the differentiation of this or
So
gradient of this?
would you use that formula if the a is symmetric, then you can use 2x to the power ta.
A is a vector.
Yes, sir.
A is a vector. So symmetricity does not hold in vector.
Okay.
So anyone can help me? A transpose x, B transpose x. See, these are A transpose x is a scalar, B transpose x is also a scalar. So entire is a scalar, product of scalars. But x is a vector, and A also vector, B is also vector. So I need to differentiate f with respect to x. Can anyone help me? Yeah?
No, sir, we don't know.
Yeah?
No, sir, please tell.
See, if you take A transpose, take the first term. A transpose x will be 1. B transpose x. Now problem is, it is perfectly fine because B transpose x is the scalar. Multiply scalar by the vector is perfectly fine. So it is A transpose next bracket B transpose x, then plus A transpose x next bracket B transpose. That's all. You have to keep in mind the multiplication is feasible. If they cannot multiply, then your derivative is not correct. You have to keep this in mind. So first bracket only A transpose, second bracket B transpose x plus A transpose x in the first bracket multiply by B transpose. So this is the derivative of this. And take the transpose of this, it with the gradient. Okay?
Okay, sir.
Fine. Now, if the second partial derivative of the function are not continuous, then the Hessian, which is capital F, need not be symmetric. Now I have given a function f of x is equal to x1, x2, x1 square minus x2 square upon x1 square plus x2 square, x0 to 0 and 0. This function is not continuous. Second derivative is not continuous. Oh, sorry, first derivative is not continuous. So I have taken the first derivative of f with respect to x1 with respect to x2. We got this one. Now, Now, see, when you take the direction derivative or the partial derivative, you go either x direction or y direction, or if you have multiple directions, then you generally represent x1, x2, x3, xn. So if you see the second line, del f x1 0, del x2. So I am going along the x1 direction, x1 vector. So it is 0. If it is 0, then I take the second derivative with respect to x1 square 0. Now take the with respect to x2. In the direction of x2, with respect to x1, it is minus x2. And you take the again derivative with respect to x2, then you get minus 1. Similarly, del f 0 x2 transpose x2 0. You take the second derivative 0, and you take the del f x1 0 x2, means along the x1 direction, along the x2 direction. You have to move and you have to find the derivatives. So at 0 0 you will get 0 minus 1 0 1. It is not symmetric because the second partial derivative is not continuous of this function. That's why it is not symmetric. So this is the example which shows if the second partial derivative is not continuous, then the what you call Hessian need not be symmetric, which is there. Now, what are the conditions for the optimization? See, in 12th class we have understood first derivative, take first derivative, make it 0. Whatever value you get of the variable, then take the second derivative of the function, evaluate that second derivative at this value, greater than 0, it is minima, less than 0, it is maxima. Since we are considering now vectors, not the scalar, so we have different conditions. Of course, quite similar to the positive definite, positive negative definite, or semi-definite. Can you see it?
Sir. Yes,
Yes,
sir.
sir.
Now, this is the straight line. X is the point on the boundary. Now, if I take any point in the neighborhood of X along the D2, it will be outside of the domain. If I take any point, X is on the boundary. If I take any point in the neighborhood of X in the direction of D2, it will be outside of the domain or inside? See, I take some point in the neighborhood of X. X is on the boundary.
It's outside, so
It will be outside. So it will not the feasible direction.
yeah.
Now take the D1 direction. Can you see the D1 direction?
Yes, sir.
You take any neighborhood of X, and that point will be in the interior of the domain. Yeah.
Yes, sir.
So this is the feasible direction. D1 is the feasible direction, but D2 is not the feasible direction. So when you need to find whether maxima is on the boundary, in that case, you need the feasible direction. So in this figure, D1 is the feasible direction because the neighborhood, any point in the neighborhood of X, X is on the boundary, lies in the domain omega. That's why D1 is the feasible direction. But if you take the any point along the direction D2, that point will not lie in the interior of the domain. That's why D2 is not the feasible direction. Clear? Hello?
Yes, sir.
Fine. Now the first order necessary condition, like first derivative is equal to 0. Omega is the domain of Rm and F is continuously differentiable. Then X, if X is the local minimizer of F over omega, then for any feasible direction, we have D transpose del F X greater than or equal to 0. See, for minima, first derivative has to be for minima.
Greater than 0.
But if you see, it is greater than or equal to 0 because you have to consider the boundary point also. Greater than 0 is applicable only when it is inside the domain, not on the boundary. But your minimizer may lie on the boundary also. In that case, it is greater than or equal to 0, not exactly 0. If it is strictly 0, then it lies in the interior. If X star is the local minimizer of F and X star is the interior of inside the omega, then strictly 0. Sorry. First derivative is 0, right?
Yes, sir.
First derivative is 0. But if it's the previous equation in the feasible direction, it is greater than also 0. But when this x star is the interior point, it is exactly 0. This is the extra we have added what we learned in 12th class. First derivative is 0, second derivative is negative for minima, for maxima, and greater than 0 for minima. But first derivative here is 0 only when it is the interior point. It is, if it is on the boundary, then it can be greater than or equal to 0. And direction is the feasible direction. Clear?
Yes, sir.
Any doubt?
No, sir.
Okay, fine. Now f is the given function x1, x2, x3, and d is the given direction 1 by 2, 1 by 2, 1 by square root 2 transpose. It is a basically column vector. Can you find the directional derivative of x in the direction of d? Hello? Can you find the direction derivative of f in the direction of d? You take the first derivative, partial derivative. Basically, you need to find the gradient of f. Gradient of f. And then you take d transpose multiplied by this gradient of f. You will get the direction derivative of f in the direction of d. So what is the differentiation of this? These are the scalars. X is a vector in 3D. So if I take d del f upon del x1, it will be x2, x3. If I take del f upon del x2, it is x1, x3.
X1, X3 plus
So I will get
X1,
three
X2.
components. One is x2, x3. Second component is x1, x3. Third component is x1,
X1,
x2.
X2.
So it is a vector. First component is x1, x2, x3. Second is x1, x3. Third component is x1, x2. And this is the column vector. Multiply by the b transpose. So it will be half x2, x3 plus half x1, x3 plus 1 by square root 2 x1, x2. This is the direction derivative of f along this vector. Clear?
Yes,
Any
sir.
doubt?
Yes, sir.
If doubt is there, I will explain again.
No, sir.
No, not clear or no doubt?
Yes, sir.
No, doubt is not there or clarity is not there. Which one?
No, clear.
Not
Clear,
clear.
sir.
So
Clear,
no
sir.
doubt. No
No
doubt
doubt.
there.
Okay, fine. Thank you. Can you see this? F of x is equal to x1 square plus 0.5 x2 square plus 3x2 plus 4.5. x1, x2 are greater than 0. Basically, they belongs to the first quadrant. If I take R2, x1, x2 greater than 0 means first quadrant, right? First quadrant.
Yes, sir.
Okay. Take the partial derivative of f with respect to x1. It is 2x1,
Plus 0.
2x1 only.
Yes, sir. 2x1.
Yes, sir.
Other
2x.
terms become 0 because x2, x3, x2's and constant will turn to 0
Yeah.
if we take with respect to x1.
And with respect to x2, it will be x2 plus 3.
0.5 into 2. That is
Into
1
2.
times x2.
x2 plus 3.
Yes, sir. x2 plus 3.
So first component is 2x1. Second component is x2 plus 3.
x2 plus 3.
So if it is maximum minima, then make it 0. So it means x1 0, 2x1 is equal to 0, right?
Yeah.
See, first derivative is 2x1.
Yes, sir.
First component. Second
First component
component
to
is x2 plus 3
plus 3.
is
x2
equal to
plus
0.
Yeah.
Yes, sir.
So it will be 0 minus 3. 0 minus 3. See, x1 is equal to 0. First component is 0 and second component is 0. Right?
Yes, sir. x2 plus 3 is equal to 0. That's the second component.
Yeah, it means x2 is equal to minus 3.
Minus 3.
Yes, sir.
But this will not lie in the domain. See, x2 are positive.
Yeah,
Yes.
they're in the first quadrant.
Yeah. So simply consider x1 is equal to 0, x2 is equal to 0. Let us see whether it is a maximum or minima.
Yeah,
Take
we have to
the,
take the second order derivative.
yeah. How much? Take the any direction. You find the gradient at 0. Find the gradient. It is 2x1, x2 plus 3, right?
Yes, sir.
And make, what we should do? Take some direction and multiply by this. If you see the previous one, what you are getting, this one or this one? Get the equal to 0. See, take any vector.
Second one.
See, there are two conditions: d transpose del f x star get the equal to 0, del transpose del f x star is equal to 0.
Wait,
There are two conditions, right?
Minus.
So let us see 0, 0 only.
Yes.
Okay.
It's the second condition. No?
So at 0, 0, what the condition? At 0, 0, take the first derivative.
क्या था पीछे स्लाइड दिखाओ सर फिर से
नहीं नहीं, इसका फर्स्ट डेरिवेटिव निकालिए ना, ग्रेडियंट निकालो पहले तो। ग्रेडियंट 2x1 x2 plus 3, right?
Yeah, 2x1 and x2 plus 3. These were the two first
And at
grade.
0, 0, at 0, 0, it is 0, 3,
Yes, sir.
0, 3, right?
0, 3.
Okay. Let us see. No, no, we are considering a point 1, 3. At 1, 3, can you find the value of this gradient? Can you find the value of at 1, 3? See, first 2x1, it means 2,
2 and
2, 6.
6. 2,
2,
6.
6. 2,
Yes,
6,
sir.
right?
2, 6. Yeah.
2 plus.
Okay. What the first order necessary condition? Can you see the first order necessary condition? This one.
It's greater than 0.
If it is at the boundary, this. If it is a low interior, this. So take any feasible direction 0, 0, multiply this. See gradient multiply by the vector 0, 0. Can you get anything? So you got 2, 6, right?
2, 6.
Right?
Yes, sir.
Now along this vector, so take transpose multiply by 2, 6, right? See, d transpose is 1, 3, right? Vector is given.
Yes, sir. 1, 3.
This vector is given to me. Okay?
Yes, sir.
And the gradient at this point is 2, 6.
6.
So find the value of this. It is positive or 0? See 1, 3 transpose 2, 6. It is a row vector, a column vector. Multiply them. It is positive or 0? 1, 3 row vector, 2, 6 is the column vector. Multiply them. Hello. Row vector 1, 3, column vector 2, 6. Can you multiply them?
20.
1, 2,
Uh,
1 into 2, 2.
plus 18.
18, right.
20.
So which condition is satisfied?
Greater
First,
than 0. First
greater
one.
than 0.
Yes, sir.
So can we say it is a minima?
Yeah, it's a local minimizer.
Greater than 0.
Yes, sir. Local minimizer.
Really? See,
Acha,
if
derivatives greater than 0 means, yeah, that should be minimum.
no. See, if x is local minimizer and x star is interior point,
Yes,
what
sir.
the point?
Interior.
1, 3. It is interior or exterior or boundary?
1, 3 interior.
Interior. So
Yes.
direction derivative should be 0 or greater than equal to 0?
So it's coming out to be greater than 0.
It should be greater than 0 or equal to 0. What should be? If it is an interior point,
It should be equal to 0 for
equal
an
to 0.
interior point.
But it is not equal to 0.
Yes, sir.
It means it is not the minimizer.
It's not a minimizer because it's coming out to be 20.
Positive.
Yeah, positive.
So 1,3 is not a local minimizer. You got it? Why it is not local minimizer? Because it's the interior point, and for interior point, D transpose
F star x should be 0.
0, but it's not
Yeah,
0.
no,
It is greater than
not.
0. So it is not a local
Yeah.
minimizer. Clear?
Yes, sir.
Second order necessary condition. Omega is the subset of Rn. F is C2. C2 means 2 times continuous differentiable. If X star is a local minimizer of F over omega and D is any feasible direction, sorry, direction is not there at X, then this is the first condition. D transpose DL Fx 0. If this is holds, means first condition. Can you see this? If this holds, then D transpose F of X star D greater than. Can you see this? This is the quadratic form.
So what's that greater, that capital F?
Hessian, Hessian.
SM. Okay.
Can you see this? F.
Yes, sir. Yes, sir.
This is the Hessian.
Second order derivative.
Yeah, second order
Dem.
derivative. So if this holds, then quadratic form in direction of D should be greater equal to 0. This is the quadratic form na, of f of star. Quadratic form X transpose QX. It is
Yes,
called
sir.
quadratic form. So quadratic form should be greater than equal to 0. If X star is the local minimizer and this condition holds. Please try to understand. This is the local minimizer. Only when this condition hold, then this should hold. F is the Hessian. It is which one? Positive semi-definite, positive definite, what? This quadratic form. Positive, negative definite. Oh, sorry, negative definite, negative semi-definite, positive definite, or positive semi-definite. Which one? Quadratic form. See, if it is strictly greater than 0, it is a positive definite. Greater than equal to 0, it is semi-positive definite.
Semi-positive definite.
Strictly less than 0, it is negative definite. Less than equal to 0, it is semi-negative definite. Clear?
Yes, sir.
So it should be positive basically. If it is a strictly local minimizer, then it should be strictly greater than 0. Second derivative should be for
Greater
minimizer
than 0.
greater than 0. Is it okay?
Yes, sir.
So this is the second condition. And F is positive semi-definite. See, this part contain minimizer boundary also. If minimizer lies inside the domain, then it is strictly greater than 0. If it lies on the boundary, then it can be equal 0. That's why it is greater than equal to 0. To consider the boundary point also. Okay? If it is strictly positive, then the point has to be interior. Okay. Can you see this? F of, what is that? Can you remove this bar somewhere? Because I'm not able to see. See this. Can you remove this? I have Kumar. Right. F of x equal to x cube. What is the first derivative?
3x square.
3x square, right? It is R to R. Make it 0, x is equal to 0, right? Second derivative.
Yes, sir.
Second derivative 6x. 6x. 6x now.
6x.
Second derivative.
Yes, sir.
Which is again 0. So it is not minimizer or maximizer at 0. F of x cube is not, does not have minimizer or maximizer that is equal to 0. Now see the second example. See f dash 0 0, f double dash 0, it satisfies the first order necessary condition. Does it satisfy? First derivative at 0 0.
Yes, sir.
What is the second order necessary condition? Second, if you see
Greater than equal to 0.
greater than equal. So second also is satisfied. See, greater than equal. Equal is there, na?
Yes, sir. Equal is there, so second order, second condition is
So
also.
second condition also satisfy. But it is not minimizer. Do you know the curve of x cube? It is going like 10x. One side going upside, other
The other
side
side
going
down.
downside.
Yes, sir.
So it does not have minimizer. So these are the only necessary condition, not the sufficient condition. Even the conditions are satisfied, still it is not minimizer. So for that we have to see sufficient condition also. Consider second example f r to r. What the gradient of this? 2x1 or minus 2x2,
Yes, sir.
and second derivative
2
2 0 0 minus 2
minus 1.
minus 1 or minus 2. Hessian is 2 0 0 minus 2. Hessian 2 0 first row, second row is 0 minus 2. This is the
Yes,
Hessian
sir.
of f, right?
Yes, sir. 2 0 0 minus 2.
It is positive definite, semi definite, positive negative definite, positive negative semi definite. Oh, sorry. Which one is? The Hessian is positive definite, positive semi definite, negative semi definite. Any idea? How to check it?
Eigenvalues should be negative for
Yeah, negative definite.
negative definite.
For positive definite, they should be positive.
Positive eigenvalues.
So, what are the eigenvalues of this?
2 0 0 minus 2. 1 minus 2 is there.
2 and minus 2.
Yes, sir.
It is neither positive definite, neither
No.
negative definite. It is indefinite matrix.
Yes, sir.
Sir.
Got it?
Okay, sir. Yes, sir.
So, it will not help to find maximum minima. So, 0 satisfied for this Hessian f is, can you see it?
Yes, sir.
It is indefinite.
Yes,
Neither
sir.
positive definite, neither negative definite. And 0 0 is not a minimizer because Hessian cannot be decided. If it is positive definite or positive semi definite, we can say it is minimizer. If it can be, may not be, it may have. But here we have two eigenvalues, one is positive, one is negative. So it is indefinite. So nothing can't be say. Second order sufficient condition. Let A belong to C2. C2 means twice continuous differentiable in a given region in which X is the interior point. Suppose for the gradient of f at x equals 0, this is the first derivative, right?
Yes, sir.
And
Yes,
second
sir.
derivative greater than 0. Can you see it?
Yes, sir.
This is,
Yes,
I
sir.
think. Then x is the strict local minimizer. You can see strict because it is interior. Okay. So if these two conditions are satisfied, then x is the local minimizer. So this is the sufficient condition.
Sir, in the first condition that D is not there.
What is that? B?
In the first condition, D is not there.
Uh, uh,
Earlier
see
we had D
gradient.
transport.
See gradient. We have to see gradient, not the
Just the
derivative.
gradient. So that's sufficient if you take the gradient.
Yeah.
Okay.
Fine.
Yes, sir.
Now can you see the example? F of x equal to x1 square plus x2 square.
Yes, sir.
First derivative is
2x1 plus 2x2
2x1 and
plus
2x2,
2x2.
not plus.
Okay.
At 0, 0, it is 0.
0 0 it's 0.
So first condition satisfied, gradient of f(x) star is equal to 0, satisfied.
Yes, sir.
First condition,
Yes, sir.
grade f of x star is equal to 0 because 2x1 comma 2x2. If I put x1 x2 is equal to 0 0, then I will get 0 0.
Yes, sir.
So gradient first condition is satisfied. What is the Hessian?
2 0 0 2.
Right. It is positive definite.
Yes, sir. Positive definite.
So it is minimizer.
Minimizer.
So 0 is the minimizer. Can you see it?
Yes, sir.
So it is minimizer. See golden section method. To find the minimum maxima, generally what we do, we take the first derivative of the function in scalar case. make it 0, then take the second derivative, evaluate that second derivative at the given point. If it is positive, then it is minima. Less than 0, it is maxima. True?
So we are
Hello.
not considering the point of inflection where it is exactly equal to 0, the second order derivative.
Where?
In any of the optimization cases, there's another condition.
No. See,
yeah.
point of inflection, basically that neither maxima nor minima.
Right.
So we are not considering that point.
We're not considering that. Okay.
Yeah. Now, see what we used to study in 12th classes. We used to take first derivative, make it 0, right? For the
Yes,
scalar
sir.
functions.
Yes, sir.
And whatever value we get, we take the second derivative of the function and evaluate that second derivative at that value. If it is greater than 0, we get minima. If it is less than 0, we get
Maximum.
maximum. I don't want differentiation at all. I do not want differentiation at all, either first or second. But I need optimum value. So this method helps to find that point. In fact, this method does not find a single point. It finds an interval. It finds an interval in which that point lies. You can reduce the size of the interval as much small as you want, but accordingly the complexity will increase, the computation will increase. But it does not require any kind of derivative. Point clear?
Yes, sir.
This golden section method try to find out an interval which contain the minima point or maximum point without calculating first or second derivative. You can make the interval in which the minima or maximum lies as small as possible. But if you take further small, then your complexity will increase, calculation will increase, computation will increase. Clear?
Yes, sir.
Yes, sir.
Okay, let us move how to proceed. So generally we are assuming there is only one minima in the given domain in which we are considering the function. Okay. So what we do, we consider the interval a0, b0. Can you see a0, b0? This is the interval
Yes, sir.
line. So I divide this interval into two parts. It means I choose two internal points inside this interval which satisfy this condition. A1 minus A0 is equal to B0 minus B1 is equal to rho times length of the interval. Can you see the equation?
Yes, sir.
See, within the A0 and B0, I need to find A1 and A2 such that length of A1 minus A0 and B0 minus B1 is equal to rho times length of the interval. And we take less than half interval length. Otherwise, it will overlap and it will
Yes,
create
sir.
the problem. So rho is always less than half so that interval do not overlap. Okay?
Yes, sir.
Now, so we have find 2 points A1 and B1 inside A0, B0, right? Using this, you can take rho less than half, any value you can take rho. Using that rho, you can find A1 will be A0 plus rho times B0 minus A0, right? A1 is equal to A0 plus rho times B0 minus A0.
Yes, sir.
And B1 is equal to B0 minus rho B0 minus A0,
Yes, sir.
right?
Correct.
Now you can see A0, A1, this is the length of A1, A0, B1, B0, this is the length B1 minus B0, and they are rho times the entire length. Rho times entire length. So now you can take unit interval. There is no harm. Now, suppose FA1 less than FB1. So where the minimum will lie? Which part will lie? It means FA1 is less than FB1. It means FA1 is smaller than FB1, right?
Yes, sir.
So minimum will lie where A1 is there. So A1 is there means you can say A0 to B1
B1.
is the interval where the minimum will lie, right?
Yes, sir,
sir.
in between A0 and B1.
If A1 greater than equal to B1, then it will lie A1 to B0, right?
Yes, sir.
Now, for the moment, you can assume FA1 less than FB1. So we will consider A0 and B1 as the interval. Okay.
Okay, sir.
Now we compute A2 B2 in the A0 A0 B sorry A0 B1. We are assuming FA1 less than FB1. So our interval is A0 B1, right?
Yes, sir, A0, B1.
Okay. We have already calculated FA1 in the previous one. We have calculated FA1 and FB1 also, right?
Yes, sir.
Now you have to choose A2 B2 and we make B2 as A1 and we have to calculate A2. So A1 minus A0 is equal to B0 and B1 is equal to rho because we are taking the unit length. Okay?
Yes,
See
sir, equal
this.
to 1. Hmm.
A1 minus A0 is equal to B0 minus B1 is equal to rho because this is the unit length. B0 minus A0. Okay?
Yes, sir.
Yes, sir.
Oh, fine. So, fine. Now B1 minus A0 is equal to B0 minus A1 is equal to 1 minus rho. Do you agree with
Yes,
this?
sir. Yeah.
Say this part. This is a 1 minus rho. If it is rho, if this is rho, this is 1 minus rho. Remaining part. Total is 1 na?
Yes, sir.
Total is 1.
And if it is rho, then other part is 1 minus rho.
Correct.
Fine.
1 minus
Now,
rho.
so rho B0 minus A1 is equal to B1 minus B2. 1 minus 2 rho. Do you agree with this? See, B0 minus A0 is 1 minus rho.
Yes, yes, sir. Yes, sir.
This one.
B1. B1.
This is B1 minus B2. B1 minus B2 will be how much?
1 minus rho.
Because A1 is B2. See, at each point, we need to calculate only one value. So A2 coincide with B2. Next time, other one point coincide with this. So rho times this will be this and this will be rho. Now you will get rho and this is 1 minus rho is equal to 1 minus 2 rho. Can you see this? Rho times 1 minus rho is equal to 1 minus 2 rho. Rho times 1 minus rho because B0 minus A1 is rho 1 minus rho. Rho times 1 minus rho and it is 1 minus 2 rho. Can you see it? Check it.
Rho times
Yeah.
1 minus rho is rho minus rho squared.
See,
Rho times 1 minus rho would be rho minus rho squared.
that I will write. But you check this rho times B0 minus A1 is equal to B1 minus B2 is equal to 1 minus 2 rho. It is okay or not? If it is okay, then fine. Check this. B1 minus B2. B1 minus B2. Yeah? No? Because in this interval, A0 B1, we have to find A2 B2. Okay? A2 will be B1. No, sorry. A2 will be
B2.
A1 will be B2, right? So we need to find A2 with this condition. So A1, A0 is B0, B1 is rho, right? From this. From this, because this is one. A1, A0 is equal to B0, B1 is equal to rho only. Okay?
Yes, sir. Yes, sir.
And we have to consider A0, B1 interval only. And A1, B1 is 1 minus 2 rho. A1, B1.
Yes, sir. Yes, sir.
Because this is rho and this is also rho.
Yes,
So
sir.
1 minus 2 row.
1 minus 2 row. Yes, sir. Intervals. Yes.
So row B0 minus A0, B1 minus A1 is this. So
1
1 minus
minus
2.
2.
So row 1 minus row is equal to 1 minus 2 row. If I simplify this, I will get row square minus 3 row plus 1 is equal to 0. Is it okay?
Okay, sir.
Yes, sir.
The row is equal to is 3 minus square root 5 on 2. Okay?
Yes,
And
sir.
1 minus row will be, can you see this? Is square root 5 minus 1 by 2. And this is called golden number. This is called golden number. Basically, if you see the face of a person, if the person face satisfies the golden ratio, it is point something. If you see, rho is 0.38 and 1 minus rho will be 0.6 something something, right? 6.2. If the
Yeah.
breadth and height of the face satisfy the golden ratio, 1 minus rho, that is supposed to be the best, beautiful face. See, when you see the contest is there, no? So they measure that also, golden ratio. If the face breadth and height and width satisfy the golden ratio, 1 minus gold row, that is supposed to be the most beautiful face. That's why it is name of the golden. Yeah. Now, it satisfies on condition is smaller interval divided by larger interval is equal to larger interval divided by entire interval. And this is called golden section rule. That's why the name is golden section. How many? See, every time you are reducing the interval, right?
Yes, sir.
Yes, sir.
So you can further reduce the interval, but you need more computation. So you can find a interval as small as you want in which the minimum lies without calculating first derivative or second derivative. Right? Now, in n step, it reduces the range up to this 0.618 to the power n. As you increase n, it will reduce. See, n square, it will be 0.36 something. If you take n is equal to 2, square
Yes,
of
sir.
this will be 0.36, around that, right?
Yes.
If you take n cube, it will further reduce. So what
1 point.
what size you need of the interval in which your maximum and minimum lies? Depending on that, n can be determined. I will give the example. Can you see this? See,
Yes, sir.
this is the initial interval. It is not a unit interval. We will make a unit interval, and we need the minima in the interval whose length is 0.3. Can you see this?
Yes, sir.
So what we do? See A0 B1, A0 B0, right? Hello.
Yes, sir.
A0 B0.
Yes, sir.
Now, if you want to have this 0.3 length, then 0.618 to the power n less than equal to 0.2 upon 2. See why we divide by 2? Because interval not a unit. If I divide by 2, I will get the unit interval, right?
Yes, sir. 2 by 2
That's
will be 1.
Yeah, that's why to make the interval unit, I divide by 2. So if you solve this, you will get n is equal to 4. So to find the interval in which your minimum lies, for this range, only 4 iterations are sufficient. This point is clear?
Yes, sir.
Yes, sir.
You further calculate, then you can further reduce, like 0.1, 0.01. You can further reduce the interval range, but computation will increase. But for this range, n is 4. Now, we evaluate f at 2 point intermediate a1, a2. a1 is equal to a0 plus rho b0 minus b1. We can calculate it. Hello, क्या हुआ? See, b0 is 2, a0 is 1, right? Rho take any value less than half. You can take 0.3 or something. B1 is equal to A0 1 minus rho B01 is A0. Is it okay?
But sir, are we taking B0 minus A0 as 1 unit interval, right?
No, we will divide this
Okay.
by 2.
By 2.
We are taking as it is.
Yes, sir.
See, 2 has been used here to find the value
For
of n.
computation of iterations.
Yeah. So A1 is okay. A0 rho times B0 minus A0. What happened? A1. Can you see this? With the see A1 B0. You need A1. A1 will be A0 rho times this one. See A0 this point. Can you see the line?
Sir.
A0 is there. You have to add rho times A1 B0. You will get A1. And for B1, you have to get 1 minus rho times the interval length. Hello. See, A1 will be A0 plus this length. Can you see
Yes, sir.
A1?
Yes, sir.
A1 will be A0 plus
A0
this
plus,
length.
yeah.
Right?
A1 minus A0. Yeah.
And this
That
is
length.
rho times length of the interval.
Yes, sir. And the other one is 1 minus rho times
1 minus times, right?
the length of the interval.
So A1, B1 is okay.
Yes, sir.
Sir.
Now you find the value of this, whether it is greater than 0 or less than 0. F A1 is minus 24, 26. F B1 is this. So it is the A1 F A less than or F B1 less than? Which one?
F A1 is less than
Even
FB1.
yes.
A1 is less
F
than B1.
A1 less than F B1, right?
Yes, sir.
So it will lie A0 to B1,
Yes, sir.
right?
Yes, sir.
It means 0 to 1.263, right? A0 to B1, 0 to 1.263, right?
Yeah, 236.
236, right? Since AF of A1 less than, it means X star lie A0 B1. Do you agree with this?
Yes,
Yes,
sir.
sir.
Now the new interval is 0 to 1.263. Choose 2 points. Now choose B2 coincide A1 as we did earlier, and F is evaluated at A2. We need to find A2. Is it okay?
Yes, sir. B1.
Now you calculate value of F at A2. F A2 is minus 20.10. F B2 is F A1 this. So F A2 greater than F
A1.
B2.
B2. Correct.
So it will lie B1, it will lie A1 to B2. No, sorry. A2 B2 B1. A2 B1, no?
Yes,
Right hand
A2
side
B1.
interval. Which one?
A1.
A2 to
A1.
B1.
See,
A2 to B2.
see, if it's left hand side, we take the initial value.
Yes, sir.
A0.
And it is right side, then we have to take the last value, which means B1. So it should
A0
be A to B1, no?
Correct. A2 B1. B1 is the end point. So from
Yeah,
A2
it's
to
a
B1.
A to B1, right?
A2 B1. Yeah.
Right. So now interval had reduced to this one,
0.47 and 1.2.
right? So then you have to calculate further
Iteration 3.
points. Choose A3 as B2, and we have to calculate B3 is equal to this, right?
Yes, sir.
Calculate the value of A3 is equal to FB2 is this, FB3 is equal to this, which means less. FB3 is greater than FA3,
Yes, sir.
right? So left side, right side.
Left.
FB, right, left, because FA3 less than FB3, so left hand side. So it will lie between A2 B3.
Yes, sir. The 1 point is 1.4.
0.4, 0.
A to B3 या B to A3? No, it is left hand side means lower bound is fixed means B2 lower bound is A to B3. A to
A to
B3,
B3. Yes, sir.
right?
A to B3.
Because if it's left side, then lower bound is fixed. Same
A2.
earlier
Yeah.
one. If it's right
Yes.
hand side, then upper bound is fixed.
Lower bound is 1.4, I think.
So it belongs to A to B3, right?
Yes, sir. 0.4 and
Fine. Can you
Yes,
see
yes,
sir.
sir.
the
Yes, sir.
interval?
Hmm.
Now choose B. It is FA2. So again, it is B2 is A3, and we have to calculate A4 is this, right? So FA4 is this, FB4 is F3. So
No,
it
A4
may
is greater. FA4 is greater, so this
greater
again
than.
will be
It
on the
means
right
right
Yes,
hand
sir.
side, right?
right
Right
hand
hand
side.
side, sir. Yes.
Right hand side means it has to be A4 B3. Which one? Or B3 A4? Which one? It is right hand side now.
Yes, sir. So B3 is fixed.
B3 or A3 fix?
Right hand side is B3 should be fixed.
B3 B3 means A4 B3 then.
Yeah, I think so.
Yes, sir. 0.65 to 0.9.
Yeah, A4 B3, right? Correct.
Yes, sir.
Yeah.
Did you get the interval length?
Yes,
Yes,
sir.
sir.
0.3.
Yes, sir.
It's become
So
quite
you
small.
can stop it. Otherwise, you can go further. You can make this interval as small as possible. You want, but computation will increase.
Yes, sir.
So if you see, it is 0.290, so it is less than 0.3, right? Length of the interval.
Yes, sir. Yes, sir.
Yes,
So
sir.
your solution or minimizer lies in this interval.
Yes.
So this is basically calculate the interval in which you come at the minimum or maximum without calculating a differentiation
Derivative. Yes, sir.
Yes,
derivative,
well done.
So this is
Yes.
right?
quite like bisection method, right?
It is not
Something like
exactly
that.
very similar to that. It is not
Yeah.
exactly bisection because we are taking
Yeah.
interval of different length, but similar to
Yes,
that.
yes, sir. Yes, sir. Absolutely.
Okay.
Steepest descent method.
So have you done this? How much
Yes.
time? How much time is there? Because I want to move the discrete optimization. How much time will you allow?
Until, sir, local
So you
minimum.
can continue.
I continue.
Yes, we have the next session at 2.
Okay,
So
fine,
I
fine,
think you can continue for.
okay, fine. See, if you remember, we are getting a sequence. What do we do if you remember this? Uh, we assume initial value of the solution, right? X0. Then using X0, we calculate X1 in optimization, any numerical methods. It is basically xk plus 1 is equal to xk minus alpha times del f of xk. That's the common formula for everyone. Can you see this? And you have to find alpha k that minimize this. So alpha k is the scalar using the older method which we had discussed, golden section method. You can find the alpha k. Once you find the alpha k is nothing but the at what rate you are moving toward the solution. So so you get a sequence of solutions xk, k0 to infinity, right? And in which direction you have to move. See, it is a vector. Let us say there are three dimensions are there in the vector. It means there are three directions are there in which you can move. In case of scalar, in one direction is there, right? Hello?
Yes, sir.
If vector contains three components, it means there are three directions. So you have three ways to move, either x1 direction, x2 direction, x3 direction. But which direction I should move so that I can get result, my minimizer fast. Got it?
Yes, sir.
If it is n dimension, vector is n dimension, then I got n directions to move. And I need to find which direction I should move so that I can get the result fast. That's the objective. Now, can you see this? Xk minus xk plus 1 minus xk and xk plus 2 minus xk minus 1. And they are perpendicular to each other. These are the vectors. X is a vector. So difference of the vector is again vector, right?
Yes, sir.
At a given point, this and they are perpendicular to each other. Getting my point? No,
Yes, sir. They
I
are
will tell you
orthogonal.
later. Okay. See this alpha, which we have covered, it is called the rate of what you call movement. If alpha is large, you are moving very fast. If alpha is very small, then you are moving very slowly. Right? So
Yes, sir.
what the optimum value alpha you can find out using this formula. See, if you are moving very fast, it may happen the minimizer area might be escaped, right?
Yes, sir.
Because there is a small area in which the minimizer is there. But since you are moving, your steps are very large, you can escape that area, right? But if you are too slow, then it will take more time to compute. If you move very slowly, it will take large amount of time to go to some point, right?
Yes, sir.
So alpha has to be optimally chosen. And alpha golden section method or some other method, right?
Relationship was kind of recursive. You have alpha on the right also.
See, alpha k, see, this alpha I need to find out, and at each iteration, alpha will be different.
Okay.
See, let us say you are moving, let us say some water is there, and you don't have an idea whether some pit is there or not. Okay?
Yes, sir.
So what you do, we go very slowly, right?
Yes, sir.
As you cross, as you go to the other side, you can move fast.
That's true. Yes, sir.
So at each step, whether you are moving fast or slow, that has to be decided.
Decided. Yes, sir. Got it.
When you don't know the path exactly, if you know the path, then there is no problem.
Right.
There is water, we don't know whether in front of us some valley there, some it is there, we don't know. So what we do, we move very, very slowly, right?
Yes, sir.
And once we cross that danger area, we move fast,
Exactly.
right?
Yes, sir.
So, so for each step, we are optimizing, we are getting the optimum value of fk, alpha k. Alpha k is the scalar.
Yes, sir.
No, okay. Now, can you see f of x equal to x half x transpose q x minus bx? Yeah. First
Yes,
derivative is first derivative. Q is, you can assume q is symmetric. So it is simply a qx minus b. Can you see this?
yes, sir.
Gradient of f is qx minus b. Now that are the step. Can you see the equation? Sorry. Step descent. See, this is the
The
formula.
x to the x transpose there in the first equation,
Yeah.
that would be taken as a constant.
No,
X
no.
transpose.
See, x is a vector,
Right.
q is a matrix,
Use a matrix and
x
x
is
again.
matrix.
Yeah.
So the first part is a quadratic form.
Quadratic form.
Yeah, but it is a scalar.
Yeah.
It is a scalar. See, matrix multiplied by matrix. Oh, vector multiplied by matrix, you get some vector.
Yes, sir.
Vector multiplied by vector, you will get
Either a
vector
vector
multiplied by
or a
vector,
scalar, depending
scalar.
upon.
So it is a scalar.
Yes. We're taking a dot product there. Vector.
Yeah,
Yeah.
dot product.
Inner product, so it will be a scalar.
Yeah, yeah. Got it? So gradient of f qx minus b. Can you see it? If it is the gradient of this, see how to differentiate this. I told you differentiation. Let me see where that. Can you see? Differentiation by transpose AX by x is by transpose A, right?
Correct, sir.
Differentiation of X transpose AX is equal to X transpose A plus A transpose. This is the quadratic form which we need to differentiate with respect to x. This is x transpose A plus A transpose. If A is symmetric, we get 2x transpose A. Got it?
Yes, sir.
So this will be x transpose q, 2 times x transpose q, differentiation of this.
Yes, sir.
And this is simply B transpose.
Yes, sir.
Since you have written in vector column form, there is a transpose of that.
That would be
It,
B itself.
that will be B star, and this will be qx. Q is the
QX.
symmetric.
Yes, sir.
So gradient of fx is equal to this, right? Now this is the common method used everywhere. Xk plus 1 is equal to xk minus alpha k, gradient f xk. You can assume x0 some value and start forming that place. Alpha k is to be obtained from the equation. Can you see this? Alpha k
Yes,
can
sir.
be obtained. And this is the equation which is used almost everywhere. This is the gradient. You can take k is equal to 0. So x1 is equal to x0 minus alpha 0, gradient f of x0, right? Gradient you have calculated this. Alpha k you have evaluated this. Okay. Now define 5k alpha is equal to this. This is basically xk plus 1. Can you see this? F, this is the entire age xk plus 1.
Yeah, that's the right hand side of the above equation.
Right.
Yes, sir.
One more bracket is there, should be there. Fine.
Yes, sir.
Now differentiate this. See, gradient f has been represented by gk. Okay. So x as it is. Can you see this?
Yes, sir.
Minus alpha is there and gradient is represented by gk. Otherwise, the representation will be very complex. To simply it is simply a notation, not more than that. Gk is gradient f xk, right?
Sir.
Fine.
Yes,
Now
sir.
to take the derivative of phi k with respect to alpha is a scalar. Differentiate f with respect to alpha. Is this correct? Differentiate phi with respect to alpha. Alpha is a scalar. First derivative.
Yeah, it's a product of
See the derivative of the function itself. Then derivative of the entire. See xk does not contain alpha, so it is 0.
G
So minus
minus G to the
alpha
power
times
k.
this. So is it okay?
Yes, sir. This
Now
looks okay.
f dash some x is equal to, can you see qx minus b? Del f of x is equal to
QX minus B.
Hello, Shilpa ma'am. Hello.
Yes, ma'am.
Yes,
Hello.
ma'am.
I think due to some technical issue.
Yeah, internet
Sir
was not
has
there.
Okay, sir. So, okay.
Okay, fine. See, xk plus 1 is equal to xk minus alpha k times the gradient f of xk, right? This is
Please
the
share your
standard. It is
slide.
used everywhere.
Sir, the PPT. Excuse me, sir.
No,
Excuse me, sir. Sorry to interrupt. PPT is not visible.
PPT is not visible. Okay. Uh, Chandres, Chandres. Hmm. यार वो बीच में डिस्कनेक्ट हो गया था, वो पीपीटी नहीं जा रही उधर, क्या करना चाहिए? ओपन जूम सेकंड टाइम, वो जूम तो खुला हुआ है, देखिए, लेकिन पीपीटी नहीं आ रही ना। शेयर करूँ? कहाँ शेयर?
So you can click on share the screen.
या इज इट ओके नाउ?
Yes, sir. Yes, sir.
sir.
It's visible now.
Okay, thank you, thank you. So you see gradient of fx is equal to qx minus b. Very first equation,
Yes, sir.
del f of x is equal to qx minus b. Yeah, can you hear me please?
Yes, sir.
Sir.
Okay, fine. Yeah, any query? Any question?
No, sir.
No, sir.
Okay, fine. So I have defined phi k of alpha is equal to f of xk minus alpha del f xk, right?
Yes, sir.
Alpha is the scalar. If I take the first derivative, I get f dash minus g. Is it okay? First derivative.
Yes, sir. It's correct.
Now, first derivative is given qx minus b.
Yes, sir.
So I have to put this minus b g transpose it is okay.
Yes, sir.
Make the first derivative is equal to 0 because alpha is a scalar. Alpha is a scalar, so make first derivative equal to 0. And it gives minus gk transpose gk is equal to alpha times q gk transpose gk, right? Is it okay?
Okay, sir.
So if you solve this, you will get alpha k is equal to this. In this case, if your function is quadratic, you get k is defined by gradient, transpose gradient, gradient q this. This is the optimum value of alpha. You need not to use any optimization technique for finding value alpha. Alpha can directly be calculated from the gradient of f. If f is of quadratic form. Okay?
Yes,
Shall
sir.
I move?
Yes, sir.
Yes, sir.
Okay. Okay, play. Sorry. Now, Newton method. See, for a fixed size gradient algorithm, x k tends to x star. See, as you increase k, as you compute more and more, you reach toward the optimizer, right? See, you start from x0, calculate x1, x2, x3, x4, and so on. And as you moving further, you are moving toward the minimizer. Hello?
Yes,
You
sir.
are moving towards the minimizer.
Yes, sir.
Now, alpha has the limit. It is positive 2 upon lambda max upon q. Q is the quadratic form. Remember?
So, but what's lambda x? Lambda max.
Eigenvalue of q, maximum eigenvalue of q.
Okay, sir.
So you have both the lower limit and upper limit. If lambda is equal to 0, it means you are not moving at all. Your solution will not move. You will not get new point. So alpha has to positive. So it is greater than positive 0. And at the most, alpha should be 2 upon lambda max upon q. Q is, can you see the q? Q. Can you see the q?
Yeah, it's a symmetric
X
matrix.
transpose q. So eigenvalue of this. Take the maximum eigenvalue. So 2 upon lambda max q, maximum eigenvalue of q. So alpha should lie in this range. Okay. Now let us come to the Newton method. F is a function of R and to R. Now we are taking the vector. Now expand this using Taylor series
Taylor series.
with, with respect to xk. Is it okay? See this?
Yes, sir.
So f of xk can be approximated f of x is equal to f of xk plus first derivative x minus xk plus 1 upon factorial 2 x minus xk transpose
Second derivative.
Hessian x,
Yeah.
and
Hessian.
we assume it is a qx, right?
It is
So what we do, we are taking the second up to approximation up to second order and optimize this. Take the first derivative of qx with respect to x, make it 0. Qx differentiate q with respect to x. See, this part will be 0 and this part will be 1. Hello. Differentiate qx with respect to x. First derivative of q with respect to x. See, f of x will be 0, it is a constant.
Yep.
D f of x is constant, x minus xk. So here x is there, so it will be in
1.
differentiation will be 1.
1.
Basically, to make it compatible, it will be transpose. So df of xk will be gradient,
Yes, sir.
right? Plus f of xk, if you remember, if I take the differentiation of this, is the quadratic form. It is h of
Hessian.
xk. Hessian times, if you remember, what is that? Can you see this? What is the other one? Second derivative. Second derivative. What is the second derivative of this? See, first derivative is 2 extras x transpose A, right?
Yeah.
We are assuming age is symmetric. Second derivative, simply 2A. 2A or 2A transpose, whatever you call it,
This is a 2-way.
right?
Right, sir.
So it is okay.
Yes, sir.
Derivative of this, right? Make it 0. So it gives xk plus 1 is equal to xk minus f xk inverse gk. Can you see it?
Yes, sir.
Now you compare the steepest, this one. Compare this steepest descent method. Xk plus 1 equal to xk minus alpha k gradient this. And compare this with this. Xk plus 1 equal to xk minus f xk inverse gk. Gk is gradient. So here alpha k is nothing but the inverse of the Hessian.
Yes, sir.
In case of Newton, alpha k is replaced by the inverse of the Hessian. Is it okay?
Yes, sir.
Now, how to implement this? You calculate dk is equal to minus f xk inverse gk. Then xk plus 1 is equal to xk plus dk. Simple 2 steps. Is it okay?
Yes, sir.
Now,
So,
we have assumed what is that? F is positive definite. F is positive definite, greater than equal to 0. For maximum minima, you remember?
Yes, sir.
Now, if F is not positive definite, then Newton method will not help. You getting my point?
Yes, sir.
If Hessian is not positive
Yes, sir.
definite, if Hessian of F is not positive definite, then this Newton method will not work. It means it can be negative. So any solution? See, I want to remove the negativity. Hello?
हाँ जी सर.
I want to remove the negativity. Suppose it is not a positive definite. I am talking minimizer, so I need Hessian to be positive definite, right?
Yes.
Suppose it is not positive definite, then Newton will not help. What should I do? Any idea? Any guess? In any case, I need Hessian positive definite. Suppose it is not positive definite. Can I do something to make it positive definite? See, it is not positive means some of the eigenvalues can be negative. If it is not positive definite,
Yes, sir.
some
Some
of the
eigenvalues
eigenvalues
will be
can be
negative.
negative,
Yes, sir.
right? So to make them positive, what should I do?
Absolute
No, absolute will not help
or
me.
square.
Anything else? See, some eigenvalues are negative. I want to make them positive. What can do? What I can do so that I can ensure that it is positive definite? Guess. Any guess? See, something is negative. I want to make it positive. What I can do?
Square it.
Higher
Take
order terms.
take the dot product with itself.
See, I have a matrix some of the eigenvalues are negative. Somehow I am interested to make them all the eigenvalues positive. What should I do? Simple.
Multiply with a negative
It is a matrix.
matrix. Then other terms will also become, yeah, the positive terms will invert then.
Anything else? Very simple. Simplest way. Something is negative, I want to make it positive. Something. Simplest way. See, something is negative, I want to make it positive. Simplest way. Simplest way. If something is negative, I want to make it positive. What I can do? Simplest way. Hello.
So, not getting.
See,
Sir.
see, I have, let's say, -2. I want to make it positive. What should I do? Simplest. What is the simplest operation? Multiplication,
Adding.
addition, or
Addition.
what's up?
Adding.
So add something positive
Yes, sir.
such that it become positive.
Yes, sir.
Add something that be positive so that everything become positive.
Yes,
So
sir.
you add 3 plus 3. If you add 2 minus 2, it will become positive. Yeah.
So you find the lowest eigenvalue means smallest eigenvalue with negative sign, right?
Yes,
Yes,
sir.
sir.
Okay.
Yes, sir.
Add something more than that to each of the elements,
Yes, sir.
especially
Getting that.
diagonal. And this is what this fellow did. Not more than that.
Live and watch.
This Levenberg Marquardt. He did not do. See, can you see this?
Yes, sir.
Mu k I. See, mu k are eigenvalues, na? I the identity
Yes, sir.
and you have increased the diagonal element by mu k. Can you see?
Yes, sir.
Yes, sir.
That's all. And mu k is so large that all the diagonal elements are quite large. They make all the eigenvalues positive. That's all he did. Not more than that. Hello?
Yes, sir.
That's all. And rest is same. What Newton says. So even if Hessian is negative, you can add some matrix, multiply some constant, so that all the eigenvalues of the Hessian become positive. Then I can apply the matrix, Newton method same. That is the only improvement he did. And this method is supposed to be one of the important method for optimization. Clear?
Yes, sir.
Sir.
Now conjugate direction. See, as I told you, if the variable which we are considering have n components, then there are n directions to move. See, we cannot check each and every direction. There should be some mechanism to find the direction in which I can move to find the optimum value or minimizer. Okay? So we discuss some conjugate direction. These methods, the methods based on the conjugate directions, may be considered as an intermediate between the deepest descent and Newton method. In between, these methods do not require Hessian to be computed. In Newton, we need Hessian, right? Hello.
Yes,
Yes,
sir.
sir.
In case of steep descendant, we do not require this. So these methods are in between. So let Q be a symmetric matrix n cross n. The direction 0, d1, d2, and dm are the Q conjugate. If we have di t q di is equal to 0, di transpose. Basically, one of them is j. One of them is j. Not both are not I. Okay.
Yes, sir.
So only thing you have to find alpha k. You remember this?
Yeah, steepest descent.
See alpha k. Where that? अरे कहाँ गया? See, you need alpha k. This is the simply gradient. You can evaluate this. You need alpha k. So how to find alpha k? Alpha k is given by gk transpose dk dgk q dk, and xk is equal to xk plus alpha k dk. Simple. Is it okay?
Yes, sir.
So we need to now we have to find the direction. See this. Set k is equal to 0, so you can assume x0 some point anywhere. Okay. You calculate the gradient x0 at step 2. You can do that.
Yes, sir.
If gradient is 0, then stop, we can't do anything because we cannot move any further. As direction d0 is equal to minus gradient 0, which we have already calculated. Okay. Now calculate alpha k is equal to minus gk transpose dk alpha 0. G0 transpose D0, D0 transpose Q D0. Okay. Now calculate xk plus 1 equal to xk plus alpha k dk. Dk is already we have calculated as gk minus. Okay. Hello.
Yes, sir.
Gk is equal to gradient of xk. If it's 0, stop. Then calculate beta k. Gk plus 1 transpose Q dk, dk transpose Q dk, and dk is equal to dk plus 1 equal to minus gk plus this. And this is the direction we have to move. Then go to step 3. Continue this. Go to step 3 or 1. Go to 1 alpha. 1, 1. Sorry, this is 3. This step is 3. It is wrong.
Yes, sir.
1, 2, 3. So it is wrongly written. This point, conjugate gradient is clear.
Yes.
So this is the direction you have to choose in which you have to move. And it is given by these two. Gradient.
Sir, after step 6, when we go back to step 3, we have to put alpha k plus 1 there.
We have to calculate new alpha k. See, k is equal to 0 out right now. Okay.
Yes, sir.
See the first k is equal to 0. First step. So you will get x0 initial point. You have to assume that calculate gradient at that point.
Yes, sir. That's fine.
Then
I'm
take the
asking,
direction.
it's written in the step 6. No, we have to set k as k plus 1. So when we
Huh.
go back to step 3, there we are putting
See,
g to the power k plus 1 and d to the
no,
power.
this is not. See, this is not the step 3. Step 3 is the 1. 1
What
is
I'm
there in
saying.
between.
So you see the right hand side, we have g to the power gk. So we put there as gk plus 1, right?
Yeah.
Okay.
Right. See, this is alpha k is the step number 3. Alpha k formula is step number 3.
Yes, sir, that I understood.
Fine. So
Fine,
we
sir.
have to calculate alpha k and beta k. And dk is the direction in which you have to move. And it is kind of gradient. See, gradient at k plus 1, beta times gradient at k. So there are two directions. You have to take some intermediate vector.
Yes,
You got
sir.
my point?
Yes, sir.
Gk plus 1 vector, dk another vector. You have to take some linear combination of these two vectors.
Yes, sir.
This is minus 1 times and this is beta k times. And how to calculate beta? Beta is given by this. Okay?
Yes,
So
sir.
in that way, you can obtain your solution. Any doubt?
No,
Any
sir.
question?
Fine.
Any comment? Okay, fine, no problem. See, this example I have
No,
given.
sir.
So I have given this example. You can not see the whether Q is properly written and B is properly written. It is a solved example. F of x1, x2, x3 is equal to so and so. And I have written this in terms of half x transpose qx minus x transpose b. And q is this and b is this. Is it okay or something else?
Sir, I want to ask.
Yeah, tell me.
Steepest descent I've seen, I've used it also in many this thing optimization problems, like when we are finding the minimum energy value in case of quantum chemical calculations. I wanted to know
Yeah.
where this conjugate gradient method is used. I have never come across this earlier.
See, as I told you, if vector is n dimensional, x1, x2, x2, xn, these are the component of the vector, right?
Yes, sir.
Now, I really don't know where my minimizer lies, in which direction or in between.
Yes.
Okay. So I need to guess that direction. If I move along that direction, I should reach to the minimizer.
Correct.
Okay.
Yes, sir.
So conjugate direction provide that direction in which I
Sir,
can find the
any
minimizer.
real world application where we could use?
Everywhere.
Yes, sir.
Everywhere. See, this is a very practical example, practical algo.
Yes, sir.
Suppose you have to move somewhere. Okay. Let us say you want to go from Noida to Delhi.
Yes, sir.
Sir.
Let's say on foot. So you have to move accordingly. Sometimes you move this direction, sometimes you move this direction. So which direction you have to move, it has to be decided when some try point is there or bite point is there. Right?
Right.
Yes,
Let's say
sir.
try point is there. You have to choose one direction, which is the optimum direction.
Yes, sir.
So this direction decided by alpha k and beta k.
Okay, sir.
So this conjugate direction decide which direction you have to move. It may happen you have to move in between also. Not exactly in any of the direction, but some in between.
Yes, sir.
Let us say alpha direction side, alpha 2 direction side, you have to move in between.
From given option, it try to be optimum
Yeah.
options. Yes.
Yeah. So it is very practical example. So Q and B are okay
Yes.
Yes.
Yes, sir.
from this. And gradient of G, QXB,
Qx minus b.
Yes, sir.
and this is this one, G0.
And
See, point is
yes,
given 0, 0. P initial point is 0, 0, right?
yes, sir.
So G0 means gradient at point
Initial
0, 0. It is okay. 3, 0,
Yes.
comma 1.
3
Yeah.
0.
Say put x1 is equal to 0, x2 is equal to 0, x3 is equal to 0. Is it okay or not? Tell me.
Yes, sir. Negative.
Negative? Okay, fine. So make it negative. Might be some error, typing error. Okay? Oh, sorry. So D0 will be negation of the G0 initially. Okay.
Yes, sir.
Distance.
So it will be minus 300. Okay. Alpha 0, if you see this, G0, D0, D0 transpose Q, D0, right?
Yes, sir. DZ.
G0, D0, D0, Q, D0. So it comes out 518. Okay.
Okay, sir.
And this is the basically step how fast you have to move. At what speed you have to move. Alpha at this iteration. X1 is equal to X0 plus alpha 0 D0. X0 is 00, alpha 0 5 by 18, D0 is 3 comma 0 comma 1.
301.
If we do this, it is 5 by 6, 0 comma 5 by 18, right?
So we'll have to work it out. If you could share the slide at the end, we will work it out.
I have already worked out.
Work.
G1 is equal to gradient of X1. We have calculated X1.
Yes, sir.
Calculate
sir.
the gradient. You find the value of gradient f at X1. So where is the gradient? It is 3x1 minus x3 minus 3, 4x1 plus 2x3 plus x1, 2x2 plus 3x. It is at this point. Where is the point? 5 by 6, 0, comma 5 by 18. This is the x1 point, right?
Yes, sir.
You have to find the gradient at this point. And it comes out to be this one. Minus 2 by 9, 5 by 9, 2 by 3. So beta 0 is equal to, if you see the previous slide, beta 0 will equal to G1 Q D0, D0 Q D0. This G1. G1 you have calculated. So this is G1 Q D0, D0 Q D0. And it comes out to 11 by 171.
Yes, sir.
And
0.
direction will be given by minus G1 plus beta 0 D1. And this is the direction in which you have to move. Now, one iteration is over. Calculate alpha 1. Calculate then x2, x1 plus alpha 1 D0, this one. You continue. Yeah. So it will help to find the optimal direction in which you can move to find the minimizer. Any doubt, any comment, any question up to this point?
No. Okay, sir.
Okay, then let us move.
Yes, sir.
Constraints optimization.
Hello.
Yeah.
Sir,
Yeah,
Dr.
yeah, tell
Sir,
me.
Dr. Sir, how are you, sir?
I'm not, yeah, please tell me.
Sir, actually, I have a doubt, sir.
Yeah, please.
Sir, in conjugate gradient method, there are two methods available, like linear one and non-linear one, right?
A method, you are talking method or problem? See,
No, conjugate gradient method. Again, we
see,
have two types of gradient method and non-linear, right?
see, gradient method is a method in which you use gradient. Simple, simple. So gradient is gradient. What do you mean by that? Non-linear.
No, I want to ask you that there are two types of gradient methods. Linear होता है, एक non-linear होता है.
See, all the methods which use gradients, they are called gradient methods. Depending on the problem, it may happen that sometimes you may use square of the gradient or 3 times of the gradient, something, something. But all the methods which use gradient, they are called gradient-based methods. Now, what is your question?
बस मैं ये पूछना चाह रही थी कि नॉन लीनियर में ना बहुत सारे एल्गोरिदम्स अवेलेबल है ग्रेडियंट मेथड में.
See, gradient में भी बहुत सारे हैं. Gradient, the methods which use gradient is called gradient based method. So how to calculate gradient? This is the one aspect. How to calculate the rate of increase alpha? According to your gradient method, will be different.
Okay, okay.
Okay.
Okay,
So
okay.
this is the class of gradient methods. It is not a
Okay.
single method. It is a class of gradient methods. Okay.
Okay, sir. Thank you, sir.
So This is the constraint minimization problem or optimization problem. You have some constraints. For example, H is a function Rn to Rm and given this. If H of x is equal to 0, then it is a equality constant. If less than equal to 0, then equality constants. So what we do in this case, we follow very similar similar approach what we have done so far. Only thing is how to incorporate these constraints so that it becomes unconstraints problem. Everything same. What we have done. Now let us see. A point x star satisfying the constraint. See, they are n constant x star, h x star, m. They are m constant is said to be a regular point of the constant if the gradient vector of these constraints are linearly independent. So first thing is the point has
Yes.
to be regular. In
Yes,
this
sir.
case, they have to be linearly independent.
It means, sir, कि all like if we talk, कि all trends are on the same around or same directions. Sir.
No, 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 no. See, linear independence, one possibility is you can say at 90 degree, all the vectors are at 90 degree. So they are
O-
linear independent,
Okay, sir.
x,
Okay,
y,
sir.
z.
Okay,
If
okay.
there is a high dimension, then we cannot visualize,
Okay, sir. Yes, sir. Exactly. Yeah.
right?
Yeah.
So these points are linearly independent. And we have to calculate the Jacobian. Jacobian is nothing but the first derivative of, see, H is a vector now. H is a vector of vectors. Like
Mm-hmm.
H, capital H is equal to, bold H is equal to H1, H2, H2. Can you see this?
Yes, sir.
So if I take the differentiation of H with respect to X, then I have to take differentiation of each of the component of H. And differentiation each of the component is nothing but the gradient each of the component. It is okay?
Yes.
Okay. So we have the equality constants, and these constants define the surface. They might be in 2D, 3D, depending on the how many dimension you are considering.
Okay, sir.
Okay. Then you have to define tangent space. See, in scalar case, we never had the tangent space. We have only tangent. But here we have tangent space. And it is the surface x belongs to Rn, h of x equal to 0 is the set y such that derivative of h at that point into y is equal to 0. This is called tangent space.
Okay, sir.
Collection of all the vectors. If I multiply the derivative of h with that vector, I should get 0 vector. The set of all those vectors is called tangent space. See, if you see this one, we are starting with 0 vector origin. So what we do, we add some x star points. So b star defined as x plus x star, x belongs to t star. Now, can you see this? X belongs to RQ, h of x is equal to x1, h2 is equal to x1, x2. So there are two constants. Find the gradient.
Yes, sir.
Differentiation of h is okay? Hello?
Hello, sir.
Differentiation of h is okay? See, h1, x is equal
One,
to x. So this is the 1, 0, 0. First
one,
vector, first row.
yes,
Second is 1 minus 1, 0.
one.
Yes, sir.
Yes,
Are
sir.
they
Yes, sir. Yes, sir.
are they linearly independent?
Mm. Yes, sir.
Huh? Are they linearly independent?
Second
Hello?
one, second one is x1 minus x2.
X1 minus x2. So you take the derivative delta x1 upon delta h2 upon delta x1, which is 1,
1
delta h2 upon delta x2, which is minus 1.
minus 1, 1 minus 1, 0.
Is it okay? Are they linearly independent?
Yes.
It means all the points for S are regular points. Now, how to find the surface? If you remember, all the point T of y is equal to y such that this matrix do by h into y1 by 2. We have to find the y1 by 2 y3. So
Yes,
if you
sir.
multiply this, what is y? Multiply. Multiply this. Say 1 0 0 1 minus 1 0 or y1 by 2 y3. Vector and matrix multiplication. How much you will get?
Y1, uh, the row matrix,
And
right?
this is equal to
Y1.
0. So y1 is equal to 0.
Yes, sir.
And then y1 minus y2 is equal to 0. It means y2 is equal to 0. Yeah. See, from this 1 0 0 1 minus 1 0 y1 by 2 y3. What the value of y1 by 2 y3? Any idea?
0 0 0 0 0 1.
y3 also 0.
No, sir, it's 1.
y3 can be anything. So if you see, the
Yes.
tangent space is 0 0 comma alpha. Alpha is a real number, any real number. So this is the tangent space. Clear?
Yes, sir.
अगर कोई डाउट है तो पूछिए. Yeah. No doubt. So similarly, we can define the normal space. It is basically perpendicular to the tangent space. X star belongs to Rn, x belongs to Tx. Lagrange's condition. Suppose h is R2 be a constant function at each point x of the domain. The gradient of delta x is orthogonal to label set. Do you know what is label set? See, label set is the set of points where the function has same value. All the points such that f of x is equal to some constant c. Then that set is called label set. Hello?
Yes, sir.
Fine?
Yes, sir.
Okay. Basically, we have in terms of what you call parameterized form. So x is a x1 t1, x2 t, and t belongs to ab, some real line interval. X star is this. Then h is a constant on this interval. So take the derivative of this, it will be 0. So if we take gradient h of x this, is it okay if I take the differentiation of h of xt with respect to t? Can you see the last line just before the green?
Yes, sir.
So x dot t and gradient of h of x are perpendicular. Do you agree? X dot t means derivative of x with respect to t and the gradient of h, they are perpendicular. Hello? Because their product is 0.
Yes, sir. They're orthogonal.
Orthogonal, right? Right.
Yeah.
Delta is the gradient.
Yes, sir.
Delta is the gradient. Huh?
Yes, sir.
Yeah. Delta f is orthogonal to x dot. Now you differentiate f with respect to t. How much? Differentiate f with respect to t. It will be f dash x into x dot t. Hello.
Yes, sir.
Yes, sir.
Derivative
Yes, sir.
represented by x dot.
For maximum minimum, it will be 0.
Yes, sir.
So f dash xt and x dot t is equal to 0.
Yes, sir. So
It
that means they're
means
orthogonal. They're
it means gradient f and
x dot t is perpendicular.
gradient as they are parallel. See, this is also perpendicular to this, and gradient f also perpendicular to this, right?
Yes, sir. So they both are parallel.
It
to
means
each other.
they are parallel.
Yes, sir.
Gradient h and gradient f, they are parallel.
Yes, sir.
Yes, sir.
They are parallel means I can write one vector in other term.
Yes, sir. Using
Yes.
lambda or
So
some
this is what
parameter.
has been done. See,
Lagrange's multiplier.
del f is plus lambda time del h is equal to 0. Can you see this?
Yes, sir.
One has been written in terms of other vector.
Yes, sir.
Okay, sir.
And this is what Lagrange did. Not more than that. And this is what we do in constant optimization. See, this is the derivative of f. Lambda is the scalar, lambda is the parameter. Since it is a vector, and the derivative of this is equal to 0. And you have to find lambda star. Take the first derivative with respect to lambdas, make it 0, whatever you get it, then find this. So this is called Lagrange theorem. And I have given one example, you can see it. So oh, see, sorry, I have to take a leave because I have a PhD viva.
Okay, sir.
हाँ जस्ट मैं आ रहा हूँ अभी कितने बज रहे हैं 33 मैं अभी ज्वाइन कर रहा हूँ हाँ हाँ चलो चलो मैं ज्वाइन कर रहा हूँ लिंक ठीक है ओके थैंक यू ओके आई एम रियली सॉरी बेसिकली मेरी पीएचडी स्टूडेंट का पीएचडी एक स्टूडेंट जो है वो पीएचडी का वाइवा है सो आई हैव टू लीव इट 12:30 बजे था मुझे लगता है 12:30 बज गए हैं
Okay.
मुझे जाने दीजिए
Okay. Okay.
सो अभी मटेरियल काफ़ी था लेकिन आई हैव टू मूव
Sure, sir.
Okay.
Thank you so much. Thank you, sir,
ओके
for
सर
your
थैंक यू
valuable
सो मच
time and
थैंक यू
efforts you have invested in
Sure,
sharing.
sir.
Okay.
Thank you so much. Time and
Thank you,
efforts you have
thank you.
invested in
Thank you.
sharing your knowledge with us.
Thank you.
Yes, sir.
On Optima.
Minus the mathematic concept.
Yes, sir. You remind us the
Thank you, thank
mathematic
you.
concept.
Thank you so much, sir.
Thank you.
Thank you so much.
Okay.
Okay, sir. Thank you, sir.
Thank you, everyone.
Thank you, everyone.
We will start the next
We will
session
start
at
the
2
next
p.m.
session at 2 p.m.
Good morning to all of you. Sorry, good afternoon. Am I audible?
Yes, ma'am.
Thank you, sir. Good afternoon, all of you. Let's start the another session of learning. I welcome our speaker of the session, Dr. R.N. Rajotia, sir. Dr. R.N. Rajotia, sir, has completed his PhD from MDU Rohtak. He has served Indian Air Force at various air base stations. He has published 20 plus research papers in various journals, international and national conferences. He has guided many MPhil and MTech students also. Now I request Dr. R.N. Rajotia, sir, to share his words of wisdom. Rajotia, sir.
1 minute, ma'am. I'm connecting.
Yes, sir.
Make me host so that I can share the PPT.
Yes, sir. You are allowed to share your
Okay,
PPT.
okay.
You are clearly audible, sir.
1 minute, ma'am.
Yes.
Is my screen visible, ma'am?
Yes, sir. Your screen is totally visible, sir.
But I'm not. Okay, fine.
Yes, sir.
So, thank you.
Thank you so much, sir. Please start your session.
To begin with some of the key points that I wish to talk in this FDP. These are some basic definition of the IoT and its applications. Key statistics as on date for the use of the IoT devices. Some of the controllers that are ready for IoT applications, and we as a researchers and academicians who can make use of the potentials available in those controllers for our research areas. I will list them, only few of them. Then based on those controllers, I'll be showing a part of the sketch how the users can make use of those controllers and program them. And finally, I'll end up my talk with the Government of India initiatives for AI and the new job roles. Well, fine, we have been hearing the word IoT for a long, but its implementations has only been seen recently. What differences have happened and why this IoT was not possible in the early stages of its development and why only today? When you talk of the IoT, basically, I wish to have devices which at times are invisible. But if you go back history a bit of time, you will find devices were so bulky in nature, whether they were the electronic devices or any other devices. So making use of them for those kind of applications was not feasible. So researches went on, and now what exactly we have with us are the devices which are very tiny, which you can just throw in the environment, and the observers or the people won't be able to see their presence. However, they will be collecting the data and supplying it to their destinations. So to begin with, what exactly has made this IoT as a possible? So few of the things are its low cost and the low power sensor technology. These days, if you look at the devices, they don't operate at 230 volt or 110 volt in the Great England or the America, not even the 12 volts. And if you talk of the today, not even the 5 volt, they operate at just 3.3 volt, or in some cases, only just 1.5 volt. Then second thing is the availability or the connectivity for efficient data transmission. So you have the broadband and a huge bandwidth available for the devices to communicate. But when you talk of that kind of communication, since the devices itself are very tiny, for them to use those communication protocols, so we have to think of some changes so that we can apply those protocols there at the device ends. Then, as we know that at times the devices which you, I would use the word sometimes throw in the environment and forget it, whether you actually employed or implanted those devices in the places of interest or not. So just put them in the place and just forget. So the role of those devices will be then to collect the information from its environment and send it back to the other end for the computing. These computings, when you talk of, because the devices in itself are very limited in resources, they are the resource crunch devices. So how much computation power can be there in the devices? We need to think of that. And sometimes we use the terminology edge computing. And this edge computing can be in the devices or at the edges where these devices are connected. Then we can further make use of those, because sometimes the processing is required at the device place so that the decision can be taken faster. So the other cases can be that you send the data to the cloud. Now in this process, when the devices are collecting data, we can communicate with the cloud, one, with the raw data that is collected, process the data at the cloud, and then depending upon your application, that application takes the decision and further course of actions are done. So in this whole process, what exactly is happening is you're overburdening the bandwidth. So instead, if this could happen, that the devices could process the data at their end and then transmit it over the cloud. So the key decision points can then be taken with the data that is available on the cloud. So this will reduce the congestion in the bandwidth and better utilize the resources. Well, with that said, then comes yet another thing. We're talking about the IoT. because the devices which were available to us, if I cite one example, I'll be showing in the coming slide. Controller boards. There are various type of controllers available by different manufacturers. And some of them are available in our labs. So if you talk of these controllers itself, these controllers are very bulky. And in many of the cases, though the name, when we say controller, they are dedicated only for one type of applications, only single application devices. But how much single application can be done in those devices? That is a matter of concern. Let's say you're talking of the machine learning. Machine learning involves lot many steps, right from gathering the data, then pre-processing the data, and all the further stages of processing onto the data before a decision can be taken. So all those stages, maybe the cleaning of the data, or then further all these steps, all these steps require maybe different applications, different use cases. Whether those many use cases are feasible on these tiny devices, that is a matter of concern. We need to see, because controllers are available with us, but what type of controllers are required for the IoT applications? We need to definitely discuss those. What facilities, what features those controllers should have. Because ultimately, when you talk of the IoT, it's the internet and the things which can speak. A simple example could be, if I say my tube light goes off and it speaks, hello, mister, I'm off, please replace me. Yes, I will say then we are thinking of the IoT application. But that simple, a dumb tube light, in that case, has to know its status and also take some decision whether to communicate with the admin or not, so that the admin people, they either in the automated mode or in the physical mode can come and replace the tube light. So there can be number of such use cases. So this machine learning and analysis, so this is just an advancement of the machine learning and analysis technology, and accesses to various massive amount of data stored in the cloud. It allows the IoT development companies to gather insights faster and easier. Then is the buzzword, that is AI, is a conversational artificial intelligence. Well, we can think of what AI is in a broader sense, and then this as a superset. Then think of what exactly other things are required. So we say the intelligence is there, but whether my machines can understand it or not, whether my machines can react to it or not, whether my machines can take decisions and ask for certain services, that would make this as a conversational AI. So this could make use of the NLP to IoT devices and make them attractive and affordable. And with those many terminologies said, the low cost, the low power sensor technology, connectivity, the cloud computing platforms, machine learning, and the conversational AI. Now with those many things, then I would say the people have found out the answer, what exactly the IoT is. So from all these terms, few things that we can take away from this discussion is that we are talking of the things. Second is we are talking of the connected things. Third, mere connection is not enough. These devices should be able to listen the environment, sense the environment, transmit, and maybe if required, do some kind of actuating operations. And if all those things can be done, then we are at the right place and say that, yes, we are onto the IoT. So this gives me a confidence to define what an IoT is. So it refers to a collective network of connected devices. Along with this, a collective, just read it again, it says it refers to the collective network of connected devices and the technology that facilitates communication between the devices and the cloud, as well as between the devices themselves. Well, this is not possible without a lot of research work and the manufacturing, which led to the miniaturization of the chips and the high bandwidth that is available to us. So this would include the smart devices. Smart devices, I list on only a few of them, but you can just think of anything. It's like a smart TV, security camera, controllers, exercising equipments. It's not merely the exercising equipments. I'm talking of the equipments which are smart equipments, which can sense. I would say, okay, I'm sitting in this chair and delivering your lecture. My chair is not smart. If I say my chair is a smart chair, the smart chair should understand who is in this chair. What is the requirement of the person who is in this chair? So my chair should understand, yes, at this moment, Dr. Rajotia is sitting in this chair and delivering a lecture. What kind of comforts, in which position my chair should be, it should take those kind of decisions automatically. Only then I will say the device is smart, my chair is smart. It should collect data from me. As I sit in this chair, it should collect my information. What is my posture? Whether I'm just placing my hands on the chair arms, and my chair arms then collect the information as my hands comes into contact with the arms of the chair. It collects my, let's say, temperature, it collects my blood pressure, and so on. And alarms me, yes, Dr. Rajotia, be careful. You are getting older. So this is how exactly we are talking about the smart devices. It collects data from its environment, user inputs, or the usage patterns, and communicates data over the internet to and from its IoT applications. The device is available. Making the chair smart is not enough. It should communicate the data available it has collected to an application. And this is where the IoT application comes into the picture. An IoT application is a collection of services and software that integrates data received from various IoT devices. It further uses the machine learning or the AI technology to analyze this data and make informed decisions. This line is more important. It uses the machine learning or the AI technology to analyze this data and make informed decisions. So these decisions are then communicated back to the IoT devices, and the devices then respond intelligently to the inputs. And finally, we are living in an era where everyone has a mobile computer with them. So everything is useless unless I see that thing happening in front of my eyes on my this small handheld computer. And everyone loves working or seeing the user interfaces which are graphical in nature. So all these devices or the fleet of devices can be managed through the graphical user interfaces to interact with the user, end user, allowing the end user to take decisions, and if required, control or actuate the devices just sitting at the place wherever he is. A simple example could be, yes, I had a very urgent work. I had to leave to the city. I'm a villager. So I was in the field and I just put on my tube well. And since I had to move immediately, so I kept it on and then rushed for my private work. But since my all the agriculture equipments were all IoT based, I was not worried because I knew whenever the field is full of water, it will communicate with me. And then when I look at the mobile phone, yes, the work has been done. I'll just blink my eyes and the device understands, the mobile understands, yes, the tube well is to be put off, and it takes decision and the work is done. So this GUI makes our life very, very easier. And at times it makes us live with the applications. Otherwise, it makes, if we are into the CUI, character user interface, this would have make our life very boring and unpleasant, thanks to different graphical user interfaces that are available. I hope I'm going in the right direction, audience.
Yes, sir.
So having said this much, so that means we have built a background of the IoT. Now, since the things are available, since the applications are available, since the GUIs are available, what next? So if you look at the few application areas, though I have covered up in my previous slides, but however, to look at little more depth, what different applications the IoTs find. I'll not go much into details since these details are available everywhere. I also have taken this image from the Google and pasted it over here. So if you see the different applications are the smart cities, smart homes, healthcare applications, ट्रांसपोर्टेशन, हेल्थ केयर का मैंने एक बहुत बढ़िया एग्जांपल दिया आपको कि माय चेयर इज स्मार्ट एंड it takes care of my health as well. So it measures all the required parameters like the temperature, the other BP, etc. And it communicates to the maybe my personal doctor or to the nearest hospital. Transportation, smart manufacturing, cars. I would not say these simply as the applications, but if you can add one more word to every term that is used in this slide, I think then I would say that this slide would belong to me. Otherwise, it is, I don't know whether I infringed the copyrights or not. I would say connected cities, connected homes, connected healthcare device, healthcare systems, connected transportation, connected manufacturing units, connected cars, connected agriculture system, connected variables, and the energy management. See, ultimately, we have been talking of internet. Smartness is okay. Smart can be, Dr. Ajotia can be smart without internet. But his smartness will be seen by others if the internet is available. Otherwise, this smartness is of no use. वो कहते हैं आप अपने घर में राजी, हम अपने घर में राजी. We have to be connected. So internet has to be part of it. And things must be able to sense and speak. Otherwise, we are not into the IoT term. Things should be able to sense and speak, and such devices, maybe they may have some very little computing power as well, and connected to the internet. Only then we are into these smart applications or the applications of the IoTs. Every application that you see in front of you, since I'm talking with the learned audience, every one of you knows what exactly the meaning of all these things are. And by saying smart homes, what can you do? Or maybe what can you add on to your home so that these homes becomes this smart? I should be able to control the things available in my homes remotely. I'm coming from my office and my home is just 10 to 15 minutes away. And I thought it's a very hot summer. I should put on my AC, and the moment I go back to home, I should find my room a chilled one. I'm able to communicate with the facilities available at the homes. I wish that the moment I'm just about to enter the gate of my garage gate should open automatically. And the things likewise for each of these applications. So then only the things becomes IoT compliance. So the next few slides I'll just hurriedly say, because I understand that the things are mostly available on the internet, but I thought of sharing this as this one being latest. The number of IoT devices installed from 2015 to 2025, estimated in 2025. So estimation for the next year is around 75 billion IoT devices will be installed throughout the world. And if you see the curve, how fast it rises, see, right from 2019, or just an year pre-COVID year, where the number of devices installed were only 26 billion. So today, you are reaching to such a high figure. So this rise in graph is not an alarming graph. Rather, it's a happy graph for us, because it indicates the creation of job. The more the devices are implanted, you can think of more jobs are created in the market. And more professional who are aware of these technologies, the latest technology of AI, ML, and the other deep learning or the data sciences, etc. So those people would be required. Now, if you look at some of the major acquisitions in the IoT field, if you look at this graph in the center, so you can see the different technological companies who have acquisitions, say for ARM, The SoftBank has the acquisition for $32 billion. And likewise, you can see the last line for Ring, the Amazon shareholder is $1 billion. So if you talk of the use cases with the most investment, because IoT, as we saw, it finds applications in different areas. But when you talk of these different areas, we require people to work on these areas. We require the companies, manufacturers, or the corporates to help the development, the governments to help the development. And it is not that without the support of the government, if the government do not want the progress on a particular field, that cannot progress. Today, our country found that without the presence of the AI, we are going to die. Everything will be controlled from some other place. We need to take the proactive measures. Of course, we are already late. We'll come to what the government initiatives are in the subsequent slides. But when you look at these slides, it is not me or just academics who are to think of all these things. There are other players. There are other business houses who are just finding out what business I can try out of it. So when you look into that, so there are different use cases. See, if I say manufacturing operations, this is a business of $100 billion. If you talk about the production asset management as a business, $44 billion. Smart homes is a business of $44 billion. And the freight monitoring, transportation is a business for almost 41, again, $billion. So because there are companies to invest, because there are corporates to invest for the technologies that are being developed by the researchers, so this investment is creating a huge job market. So if there are no investors, I can think that, yes, the job profiles will be very less, job requirements will be less. This is just an example of a IoT system. Everyone knows that we need the devices, we need some kind of gateways so that the data collected can be transferred. And finally, we require the places where we can analyze and take action. So this could be in the form of the user interface. This could be in the form of analytics of the business applications, or this can be a backend systems. Well, every one of you knows I have collected this slide from the Somatosoft. Again, I've taken this slide from the Scalar Academy. So this gives us the architectural implementation in the enterprises, where you have the devices or the sensors or the actuators which are in the field, collecting data through the internet gateways, maybe if required, performing the edge computing or the fog computing, or if not, sending it to the cloud and then performing all those. So this is just basic. I think everyone knows it. So then I wish to move on to some of the platforms that are available for different IoT applications. This is yet another application that are taken from one of the research paper. And it says the IoT computational layer. So it clearly says that at the lower, I have different sensors. These are my temperature sensor. This is my BP or the pulse sensor. This is my oxygen sensor, and so on and so forth. So these sensors, they could be the devices which record our medical histories, or they can be just put into the environment for sensing the environment parameters for different applications, whether they are for the military application, for academia application, or some other applications. Ultimately, what do you see here? That these devices, these sensors, they are connected, they are all connected through maybe a simple switch, let me say. And if this switch has the capability of computing on the data that is being sent by these devices and takes some decision. Let me take a very simple example that I have, let's say, still more devices in the field to record information. And if this edge node, which has small computing power, so it does computation on the data and takes a decision, maybe making use of the decision tree. So what kind of decision it can take, whether the medical data that is recorded or received is critical in nature or very normal in nature. And depending upon the criticality of that data available, it can take some decision whether that processed data, because it has processed locally, and what processing has been done, whether the data is critical in nature or a normal. Let's say it recorded my temperature and asked whether you have a temperature, yes or no, decision tree. If it says yes, then it further recorded my blood pressure and says whether you have blood pressure above certain level, yes or no. If say no, okay, normal, then otherwise process it further. Oxygen, if the oxygen not available, something critical. And if it is critical, you require to communicate with other services. And other services can be, yes, you require some kind of communication infrastructure available to you so that your request can be sent to other places who can provide the services to the lower layer or to the end user. So this particular slide gives you a very clear picture that the computation can be at the edges where the devices are connected together. So we call this form of computation at the edge computing. Then the communication infrastructure, this can be in different forms. Then the fog computing. And one of the example, if you see here, if you see the different layering of the fog computing, I would not go into the complete details of these layering systems. I think will be known to most of you. And finally, the cloud and its different layerings. So every layer has its own importance. So you need to take decision how much computation is to be done at the edge level, what computation is required at the fog layer, there's the intermediary layer, or what different computing is required at the last end layer, that is, let me call this as a cloud computing layer. And finally, maybe if I say that user is somewhere here, user application, so that user will communicate with the cloud. So the cloud informs the user what exactly is to be done with it. If the things are done automated, so maybe the processors available here, they will take a decision in the auto mode and do the things, or maybe if it is a medical case, inform the hospital where the candidate is registered so that the ambulance will come and pick them. So many different things will happen with it. Coming to some of the boards, most of you must have seen this. This is available in my library. Normally, I keep this library ready at my desk. So since we are talking of IoT, and if you see in the first case, I have a Arduino board. This board doesn't have anything other than a USB connection, which we can use it for programming this device. Then we can make put this particular device in the application, and maybe permanently in the lifespan of this device, this will go on working the operation that is defined in its software, in its sketch. Maybe a simple example can be, I have an AC installed in my office that simply monitors the temperature, and maybe at frequent times it puts on and off the AC, nothing more than that. And in the complete life cycle of the AC, the role of this device will be only just to monitor or to sense the temperature and actuate my AC compressor on or off. Nothing more than that. But for being the part of the IoT system, these devices must communicate with the IoT, internet. The other three boards that you see here, one on the top right, it's a bottom, it is a two boards. There are basically two boards. One at the bottom, which is the same as a Arduino board, and the upper one is a shield. This particular shield is a PHP OCD shield. And as you can see here, in this shield, if you talk of this particular shield, so I have a Wi-Fi dongle that I have placed here in this slot, and you also have an Ethernet slot, so that this device can now be connected to an Ethernet cable as well. So it is my wish whether I want to make use of the Wi-Fi, because since the dongle is available here, connect it to the access point and transmit the data or receive the data from the other place, other clients, or connect it to the Ethernet and make use of the maybe the other Ethernet protocol. But another beauty of this particular device is this, that it has an IC over here. If you zoom it and see, this particular IC is basically a web server. I would say this particular top layer, this is a web server in itself. It is a PHP web server. So it allows you to program the front end as well. That means I can create the web pages for each of these three cases. So these three devices that you see here in different capabilities, different sizes rather. So these will act as the web servers as well. What is missing here? I have an Ethernet connection. So this device, it can communicate with any of the devices on the internet. But when it communicates with the internet, with the client, web client, what exactly is the requirement? You know how the an application communicates with the web server. So you can think of let me say I wish to connect these three devices to my mobile phone. So my mobile phone will be my client. And if I want my mobile phone to communicate with these devices, what exactly the way of communication will be? This will be a client-server model. The client has to communicate with the server, maybe in the HTTP mode. It has to request for certain services. I type onto the in the web browser 192.168.1.1. So I'm requesting the web server, which is nothing but these three devices. I'm requesting them through an HTTP protocol that please, I'm sending a GET request. I wish to get a web page. The web page is not available on my web phone. On the browser of my web phone, I will write the address of the web page that is here in this device, 192.168.5.1. So the device will listen, this server, web server will listen that request and respond to that request and send a web page for controlling my AC, for controlling my fan, for controlling the different applications, so that just with my mobile phone, I can control all those different applications. So if you look at the features available in these three devices, I have these three devices. This is the PHP OC Shield. So the next is the Node MCU. It has a, you just see, it is a Wi-Fi chip available on this IC. And the third one is, you see the size of, it's just a quarter of the size of the normal Arduino board. And third one is the 33 BLE Sense board. Mind it, if I had to build an application with a simple Arduino, I would require at least different sensors which I have to interface with the normal Arduino. And maybe with the little things available to me, I then maybe can take simply seeing the data at the serial monitor, or maybe transferring the data from the serial monitor in the form of a CSV file to computer, and then process that data available. So these devices, when you look here, I have a Wi-Fi shield available, Wi-Fi chip available here. So this particular Node MCU, this can act as a web client or as a access point or a server. This, so is this 33 Node 33 BLE Sense. But the features available on this Node 33 BLE Sense is, when you just have a physical look at these different controllers available to you in front of you, you look at this 33 BLE Sense and you find a very small ICs all integrated on the this particular board itself. And what these ICs are, these are the number of sensors which otherwise you had to physically interface, which were bulky in nature, but now they have been miniaturized and implanted onto the quarter size of this simple Arduino board. What different sensors are there? I have a humidity sensors available on board. I have a temperature sense available on board. I have a color sensor available on board. I have a gyroscope available on this chip on board, and lot many other things. And in addition, if you see here, it also has a Wi-Fi shield, Wi-Fi chip available. So that way, if you can, maybe different speakers, right, in the morning, and yesterday even I was listening to Dr. Karan and Dr. Tayyab Khan, and even the today's speaker. So different very innovative talks were given. But you know, working with the devices is a little different. And at times I would say, you should not mind my wording, because the things have already been researched and they are available in the form of the packages. And we, as the faculties at the institutions or in the academia, we are not doing much beyond those levels, because we are not into the actual physical implement. Many of us, I'm sorry to say this, many of us, I am writing a paper, but without the physical data being collected. So if you have a device like this, wherein you can collect the data, and you will be surprised to know that the tools which are used for the machine learning or the AI that we have been talking in this FDP, those tools, let me ask the audience, if I say I can install the TensorFlow as well as in this device, would it not make your life much easier? Because what exactly you require? You require the device to become intelligent. If this device can help the machine in collecting the data, processing the data, and outputting the data in the desired format, so that the machine itself can operate in that particular mode. I don't require anything to program this. Nowadays, I can program this device using my mobile phone. And let me see how many of us are actually going to modify the TensorFlow. No, many of us are not working onto it. If I say a version of the TensorFlow, which is called as a TensorFlow tiny model, it takes only few kilobytes of the installation file, and my complete TensorFlow is available here, and I can make the different decisions which are required on the platform where it is installed, not even in the edge, at the node itself. To be very to just go to that end where the computation is now possible. If you look at these 4 cases, the first one very difficult to connect to the internet. The other have made it possible. In the second case, it was with the help of a shield. Otherwise, because we know the normal Arduino doesn't communicate with the internet. But with the shield available, if I add on the Wi-Fi shield to this normal UNO, otherwise there are the Arduinos available which are coming up with the Wi-Fi shield integrated onto it. If that is not integrated, you can use this shield like the PHP OC shield. Do I have more time, or I can wind up?
So you may continue if you have.
Okay, you have the time.
Yes, sir.
Okay, I'll try to wind up very speedily.
Yes, sir.
So I hope you got an idea where we are. And let me even further say that there are certain modules available, because now we know, I need not to tell you what are different limitations of these protocols available here. There are limitations with the Wi-Fi. But if you want to overcome with those limitations, because I was looking at the topic of the FDP, that was a security. And Wi-Fi, when you say itself, is a challenge, at least to the security. What different concerns are, maybe um, we'll just see if we can throw some light onto it or not. So we were talking with these different controllers, where I said at the bottom, you have the node MCU and the sense BLE. In a nutshell, the MCU, they again manufactured by the Chinese company Espresso, comes into different forms. Here is a description of the ESP32. The one I have with me is a ESP8266. They are the low cost, low power embedded Wi-Fi and the dual mode Bluetooth chip microcontrollers. The next one, the last one in this slide, this was a controller built around the NRF 52840 controller. This is a ARM controller with the 1 megabyte of the CPU flash memory, whereas the normal Arduino has few kilobytes. So it has 1 megabyte of the flash memory, Bluetooth, low energy, BLE, Bluetooth, 9 axis of the motion sensors, color sensor, Python support, ARM Cortex M4 controller, all inbuilt into this small 256 kilobyte of the RAM. So we will see some applications, and even before we see the applications, because ultimately what these devices have, the Wi-Fi, or this device has Wi-Fi and the Ethernet both. And if I say that these devices can act as a access points or the web servers, then protocols must be there with the devices. So I must know the layering structures of those protocols which are integrated in these into these devices. I'll not go much into details because the complete audience is much aware and much and better aware than me. So I would just take only glimpses of it. And since we say that these devices are fully available or integrated with the Ethernet or the Wi-Fi shields, so that means I am now able to communicate with the outer world. And when we say outer world, these my devices can act both as an access point or as a client, depending upon how I wish to make use of these devices. If required, I can make them to act as an access point, or if required, I can make them to act only as a web client or a client for them. So if that is the things, the different protocols must be part of it. So as far as the Wi-Fi protocol is concerned, so you can see here this is part of the TCP/IP stack. Rather, just without this, in a nutshell, if you know the TCP/IP, well, fine. This is all exactly is part of it. And in just one single word, I hope every one of you understand what exactly TCP/IP, how we have gone from the reference model OSI to the TCP/IP, and cater for all the services provided by all those 7 layers with just these 4 layers. And if you look at these 4 layers, of course, there are many things more to add to it. Applications will contain many different protocols, but maybe we can end up with only few of them, because mainly at the application layer, if you think of, we are more concerned with the OSA, the HTTP, HTTPS, or maybe the DNS, or maybe if you don't want your connection to be busy in just serving you, then of course the web sockets come into the picture. I hope every one of you knows that better. Then you have the transport layer, which takes care of the TCP and the UDP. Then the internet layer or the networking layer, which takes care of all your routing, networking, etc. And at the physical layer, then, but now if you see back, let's say I have these 2 devices and I wish these 2 devices to communicate with each other. The basic requirement is available in these 2 devices. It has a Wi-Fi available here. It has a Wi-Fi available here. Though the devices are different, but this is what exactly the protocols makes different devices to talk to each other. I'm not, without caring to what type of devices are the end devices. If I say I have the HTTP protocol, so these 2 devices can communicate and can, of course, understand what is being sent or what is being received. So this is at the top layer part. But if you come down at the physical, the link layer part, where you say where the devices are physically connected together, irrespective of how you connect them. So if that is the case, you look at this diagram. I have the same board which I can make this as an access point, or the same board which I can use as a wireless station or the wired station, depending upon the type of device. If I say I have a PHP OC, which has both the Ethernet and the Wi-Fi integrated into it. So I can make the device as a wired or a wireless station, or a wired access point. So these at the link layer, So my interest is to physically connect the devices, whether you connect them with the wires or you connect them wirelessly. So we have seen with the nano boards at the bottom, they both had the Wi-Fi integrated into those chips. So Wi-Fi is available. That means at the physical layer, Wi-Fi is there to connect the two devices. But merely being the Wi-Fi doesn't mean that the two devices can communicate. For the actual communication, you need to have more than just a physical connection. So irrespective whether the access point, at times I have my device has everything to communicate with the other similar devices. But there are one or the other reason that even being available, they are not able to communicate because the services are not available. So merely having the two wireless devices doesn't mean that they will communicate. So they will provide only the physical connectivity. So that means my all devices, if I have some more devices to connect with this access point, I have, let's say, hundreds of more devices which connect as wireless stations. All of them can connect to the wireless access point, and this wireless access point can then be connected to the internet. So this can then form the edge where the devices are connected. And all of these together, they will form a local area network. This is what exactly we do at the link layer. You only build a local area network, nothing more than. Having a network, then you have to something onto it so that we can make use of this infrastructure. Government has created the roads, but unless the government give permission to ply on the roads, we can't. So there has to be something more onto these physical devices, physical connectivities, so that we can communicate with the, and there comes the next layer, that is the internet protocol layer, IP layer. So I'll not go into the details that at this layer you have the IPs, and these addresses have to be unique so that since in the field, there is no one to control who will go and configure these devices. So we have the another protocol called as a DHCP. So this will take care of assigning the unique address. And at times you need to then make use of the subnet mask so that you are actually communicating with the devices in a particular network. So where this is where the is an optional one, every one of you are aware of. Then above this, again, IP itself is not sufficient. Then I must have a MAC. And when the devices communicate, the devices do not understand each other, even though they may be knowing each other's IP addresses. You require the physical MAC addresses. I will just skip these devices. You know how to obtain those MAC addresses of the other devices through a broadcast beacon and saying, hello, Mr. So-and-so, give me your physical address. So that particular IP address device whose IP address belongs to, it will respond back to that. So these all sort of stories there in the, and this says this is a protocol, is a ARP protocol. Then we have established the physical network. Then we have the IPs and the other unique addresses available, but still you're not able to communicate. Then there comes the TCP, because I have to establish a connection. And for this, there are two protocols there at the TCP. One is the TCP, another is a UDP. I guess every one of you understands what the difference is. Let me not go into the details, and let me skip to the, then finally you have the application layer. You need to see why exactly this requirement is, why this layer, because this layer, TCP, it doesn't dictate the content that is being sent to the destination. So there must be something at the destination which can understand what kind of stream is coming to me. And this is where the application layer comes into the picture. And That's all. So this is how the story I have taken into for a small talk on to the IoTs and different features available on to the different devices available these times. And you can carry out all sort of work right from the AI, its subsets like the machine learning or the deep learnings. So all sort of, because the things have become, the research has gone to such a level where the size doesn't matter, or how the researchers compress such a huge applications like the TensorFlow, and you can install those into very small devices which are only few megabytes of memory available onto it. So that is again a area of research and understanding. I think I had a lot many other things to say, but I guess uh, this would be sufficient for the day, because otherwise it will take another an hour or so. But I think more or less I have covered the technical aspects of my talk for this FDP. And I hope I have made my best efforts in bringing you the best of the things available, and that adds to your understanding. Even though you had a lot of knowledge, but I definitely guess that something more must have been added through these slides. So if done, then I'm open for any query or any questions from the audience. Otherwise, thank you, everyone.
Any questions, please? Awesome. Okay, thank you so much, sir, for your inspiring words, sir. I want to express my sincere appreciation to you, sir. You have shared your expertise, knowledge, and valuable insights with us, sir. Thank you so much, sir.
Thank you, audience. Thank you very much.
Yes, sir. Thank you, everyone. We are done for the day. So we will start the FDP tomorrow at 11 a.m. sharp. Thank you.
So can I leave?
Yes, sir. Thank you so much, sir.
Thank you. Thank you.
Please, sir.
स्क्रीन शॉट एक मिनट